to say when everything's getting in the way? Seems you cannot be replaced, and I am the one who will stay. Oh, oh. In this world, it's just ours. You know it's not the same as it was. In this world, it's just ours. You know it's not the same. Answer the phone. Hurry, you're no good alone. Why are you sitting at home on the floor? What kind of bill are you on? Ringing the bell and nobody.
All right. May I have some attention, please? So those people who cannot see the slides properly because our dear friends use too small fonts, those people may come forward. We are not students. Please come to the first rows, and in that case you will see the slideshow properly. Okay. Excuse me. So, okay, still incoming flow. Last minute. Yep, I would like to draw the attention of the colleagues to the virtue of scientists, punctuality. Yeah, whatever. All right. Okay, we can start. So, dear colleagues, dear students here and at home in front of the screens, I would like to welcome everybody at this occasion, the so-called EMLG summer school of this conference. This conference is about liquids, molecular liquids, which means that scientists in this group are studying the behavior of liquids from the molecular point of view, using both experimental and theoretical simulation techniques. This morning we will have this summer cool. The purpose of this summer cool is that somehow bring closer to the students, to younger generations, and not so younger generations. So for those colleagues who are accidentally not so familiar with the scientific topic, but would like to understand how the presented results come from physical-chemical basic principles. So that would be the purpose of these talks given by three distinguished colleagues. The purpose would be to start a little bit longer talk with physico-chemical basics, and after that they will present their fresh results on their specialized topics. Okay, so that's the purpose of this session this morning. We're going to have three talks, and the first one is by Miguel Jorge from the University of I'm trying to pronounce it properly, Strathclyde. All right, it's in Glasgow. And Miguel will talk about porous silica materials, how they are synthesized, and very relevant physical-chemical concepts will occur in his talks, like adsorption, self-assembly, phase equilibrium. So it's going to be about how can we understand that the process of synthesis on the basis of these competing effects. Miguel, the floor is yours.
Thank you. So, the pointer. So, thank you very much for the invitation to do this. In fact, for me, it is a real pleasure to be here back in summer, having been in autumn for about 2 weeks. You know, coming back to give a summer school is something that is very invigorating for me, coming from Glasgow. So, Desha's challenge was to talk about the science, of course, but actually extend the lecture and include some information about basic principles and basic fundamentals. So I'm going to talk a bit about multi-scale modeling, and that's why I chose this topic, also because it's related to the topic of the conference, right? Devices of life and technology. And you can think of nanomaterials as a device of technology, but there's also some parallels to life, which I won't really get into, but this self-assembly from solution is really something that happens, that is quite ubiquitous. So this is outline, so I'll start to about fundamental principles of molecular modeling. For those of you who have already done molecular modeling, this will probably be quite boring, so you can probably check your email for a while, but hopefully it will be useful for some of you. Then I'll talk a bit about coarse graining and this introduction to multi-scale modeling, how we can kind of bridge the time and length scales of our simulations to attack other problems that are more complex. And then I'll go into self-assembly and the principles of computational materials design. And then I'll start with the part of the science about the work that we've been doing now over probably about almost 20 years on this topic. So I'll go through pretty much 20 years of research in about half an hour, hopefully. And then at the end, I will give you some recent updates of a new kind of model that we've been developing that involves chemical reactions. Okay, so if you want to do modeling, and this is true about any model, it doesn't have to be molecular modeling, right? So you first have to get information about the system, so you set your anchors, what do you know, what do you want to know, etc. And then you need to develop a model for the system, okay? And then you need to solve the model, so you have a simulation method, right? So this is the first difference that is very important, is the difference between a model and a method, okay? This might seem trivial to you, but actually it's incredible how many students struggle to understand this. So the model is your representation of reality. So it's translation. As an engineer, I always tell this to my students. The main goal of an engineer is to translate reality into mathematical equations and then back, okay? And so the model is our abstraction of reality into a set of simplified concepts that can be solved mathematically. Then the actual method is the way that we solve that mathematics, right? So this is true for molecular modeling, of course, but also for finite element modeling, any other kind of modeling. So I don't really have time to talk about the methods themselves, right? So this is this other step here. Just to say that there are two classes of methods used to solve molecular models, Monte Carlo and molecular dynamics. They are essentially the integrators that we use to solve the equations of statistical mechanics. The main difference between the two is that molecular dynamics is Newtonian, so follows a Newtonian trajectory, so calculating forces over time, whereas Monte Carlo is stochastic, so it's kind of based on random numbers, and they progress through two different paths, but the aim is to reach equilibrium, thermodynamic equilibrium at the end. Okay? If you want to know more about the methods, I'm more than happy to talk about them later. What I am going to talk about in more detail is the model development, right? So what we conventionally call a force field, because it defines what forces happen in the system, okay? Right, so what is a force field? A force field describes all the interactions between all the molecules or atoms or sites in your system, okay? So we need to define our molecules or our atoms, and then they need to interact with each other, right? And those interactions determine, for example, in Monte Carlo, the way, the probability of accepting or rejecting those random movements. And in molecular dynamics, they describe or they tell you how the system propagates in time over time. Okay. So in reality, of course, any interaction between two sites is a many-body problem. So you have interactions between two sites, then 3 sites, and 4 sites, etc., ad infinitum. In practice, however, anything beyond 3-body is pretty much negligible, and even 3-body interactions are quite often lumped together into 2-body interactions. And that's mostly to make the calculations tractable. There are 3-body models out there. They're quite rare, but they exist. Okay? By and large, people use 2-body models to solve these equations. So we render everything into a pairwise effective interaction. Okay? So then which interactions are you trying to represent? Okay? And here's a kind of non-exhaustive list of these interactions. So the first is repulsion. That's the shortest range. So when 2 atoms approach each other beyond a certain minimum distance, they repel. And that's just Pauli exclusion principle, right? The electrons don't want to be in the same place at the same time. So that's, of course, very short range. It only really takes place when the atoms are very close together. You also have electrostatic interactions, right? Between, you can argue that everything is electrostatic, and that is true. But what I mean by this is permanent electrostatics between permanently charged or dipolar or polar molecules. Okay, and this is a kind of really long-range interaction. We also have dispersion, right? So dispersion is also very well known, and this is happening due to induced dipole-dipole interactions. So when 2 molecules are polarizable, they approach each other, their electron clouds fluctuate, and they generate a mutually attractive interaction. It's always attractive between the 2 molecules. This is relatively short range, of course, not as repulsion, but longer range, but also still short range by computational standards. Then there's polarization. Polarization is much more complex, and in fact, my group has been doing some work on trying to represent these interactions in a very effective way, but I don't really have time to talk about that. So polarization happens when a permanent dipole or multipole induces a dipole in another molecule, and that causes, again, an attraction between the 2. But this is an inherent multi-body interaction, and so it tends to be lumped together into these pairwise effective interactions. Okay? So there are, again, ways to explicitly handle polarization in simulations. That's not the topic of my talk. We can, again, explore this later if you want. And the final interaction is when you... sorry. Oops. Apologies. There we go. So the final one is this bonded interaction. This is essentially when you build a molecule based on atoms. Okay? So you have to tether them together so that they behave like a molecule as they progress in time. So this is just an example of these bonded potentials. When you have 2 atoms bonded, let's say in N2 molecule, for example, then you would have a bond-stretching potential. Typically, these are harmonic potentials of this form here, so it's a parabola. So anything, when the molecule is at the equilibrium distance, R0, then the interaction energy is 0. And then as you distort the molecule by extending or contracting, then you pay an energy penalty. Okay? Same for angle bending. Okay, this is easy. And then torsion is a bit more complicated because different groups of 3 atoms or 4 atoms twist in different ways depending on their energy barriers, and so you normally have a more complex function which is described as typically a sum of cosines. Okay. So there are other ways of representing this. This is the most common. That's essentially the approximation is in my talk. Just show the more common ways of representing this, but there are other options, of course. So. Now, non-bonded interactions take place between atoms that are in different molecules. Okay? As I said, there are 2 types of interactions that are present in every molecule known. Okay? And that's repulsion and dispersion. So it doesn't matter whether the molecule is polar or non-polar, large, small, etc. These interactions are always there. Okay? And so we tend to lump them together into a very simplified functional form called the Lennard-Jones potential. Even if you haven't done simulations, you've heard of the Lennard-Jones potential. So this is it. This term here is the repulsion term, so r to the minus 12, very short range, and positive, okay? So the energy is positive in repulsion region. And then this second term is the dispersion energy, which is r to the minus 6, and it's attractive, right? So it's a negative energy. You put them together, you get a curve like this. Okay, so at very short range, beyond this kind of soft sphere radius sigma, the interaction is repulsive, the energy is positive. At longer distances, it is negative and attractive, but tends to zero fairly quickly. And then there's a sweet spot, this well depth, which is defined by this parameter epsilon, which is where the molecules prefer to be. Okay? So if you have, say, a Lennard-Jones liquid, you can simulate it, and you'll see that on average, the molecules will reside close to this energy minimum here. Okay? So the other small thing to say here is that because this decays very fast with distance, we normally truncate this at a cutoff radius called the RC, right? So cutoff radius. After that, there are many different ways, but essentially we render the interaction down to 0, okay? And there's ways to compensate that using long-range corrections, which again, I don't really have time to talk about, okay? There are, again, other options. This is the most common one. You can use more complicated functional forms like Buckingham or extended exponential, something like that, to represent the repulsive side. Or you can use even simpler models like hard sphere or square well. Okay? So hard sphere is just a repulsive hard sphere, okay? And square well is something that represents this attraction using a kind of square well, as defined by the name. Okay? So they're simpler, computationally faster, but normally less realistic. Okay, so we have bonded potentials, we have Lennard-Jones interactions. That describes basically any molecule. But now if you have polar molecules, you have to add something to it, right? And that's at least permanent electrostatics. You may need to add polarization or not, but at least permanent electrostatics, you need to do it. So the equation to do that is the Coulomb law, okay? So you see the interaction decays as r to minus 1, so it's very long range. Remember, dispersion is decaying as r to minus 6, and we use a cutoff. With r to minus 1, you cannot use a cutoff, okay? So you use special techniques like Ewald sums and derivatives of those to account for the missing interactions beyond the size of the typical simulation box. Again, it is something that is mathematically quite involved, but conceptually it is rather simple. So you approximate the missing interactions through a background charge, and you integrate that background charge using Fourier transforms, okay? So again, no time to go into the details of this, but just to let you know that there are techniques that are robust and well used to account for this kind of missing level of interactions. And this graph shows you just an example of the magnitude of these permanent electrostatics. So normally they're represented by assigning partial point charges on each atom, okay? So for example, in the water molecule, you'll see here, you would typically have a negative partial charge on the oxygen atom, and then 2 positive partial charges on the hydrogen. And of course, they need to balance out because the molecule has to be neutral. So those partial charges, they can be assigned in different ways, empirically or from quantum mechanics, etc. Again, this is something that my group has been doing some work on, but we don't have time to cover. But they are assigned in some way. And that gives rise to an interaction between those charges in the molecule. And this graph shows you the typical type of interactions between a water dimer forming a hydrogen bond. Okay? So you will see that these interactions down here are the attractive ones. Okay? So these are the OH, right? Interactions between opposite charges, one positive, one negative. They're all attractive. The pink one here is the one between the H and the O forming the hydrogen bond. So it is stronger than the others, of course, as you would expect. That is partially offset by the positive or repulsive interactions between the HH atoms and, more prominently, the OO atoms, right? When you put it all together and you add the black line, which is the Lennard-Jones interaction between the 2 oxygen atoms, you get the red curve, okay? So you'll see that this black curve is what you would get if you had a non-polar water model, right? And you see that, of course, as you expect, electrostatics completely dominates the interaction between water molecules, okay? You would expect that. I will tell you more about this balance between non-polar and polar interactions as we go along. But in this particular case, it is overwhelming, okay? And as I said, you can also include polarization interactions. Those are much more expensive to compute, and so essentially a choice is to use a polarizable versus non-polarizable model, and that's a very important modeling choice. But again, we don't have time to cover that. Okay, so that was in 10 minutes, more or less, a 101 of force field models. Now, in practice, what do you do? Okay, so the modeling part, I normally tell my students that the computational part of solving the problem is important, and sometimes we need to put in some effort into it. But actually, I think for me, the most important and useful part is the modeling. That's the creative part. Okay, that's when you try to again understand the physics of what's going on and translate that into a simple model that you can solve. Okay, as one of my postdoc advisors used to say, your model, and paraphrasing Einstein and others, right? Your model should be as simple as possible, but not simpler. If it is simpler, you don't get the physics, right? If it's more complicated, then you're wasting time. At the very least, you're wasting time, and you're probably over-defining, over-parameterizing your model. So how do you choose the right model? Well, the question is, first, you need to understand your system. And so the right model depends on the system you're studying. And I will show you in the research that I'm going to talk about today, the self-assembly, the right model tends to have to be very simplified, because we're having to try to access very large time and length scales that you would not be able to access with atomistic models. So that's the first choice. How detailed should my model be? And here are 3 options to represent propane. Okay, it's propane molecule. You have 11 sites. All the carbon atoms, all the hydrogen atoms in your system, and they interact with what is called an all-atom model, fully atomistic. You can simplify that. You can say, well, these hydrogens aren't really doing much there. They're very close to the carbon. This is non-polar. Let's get rid of them. And we coarse grain. That's what we call coarse graining. So we can represent it by 3 sites, which are not a carbon. They're a CH3 and CH2 group. Okay? So this is what is called the united atom approach. Okay? It's very popular, and we use it a lot as well, because in fact, there's very little lost in going from this side to that side for a non-polar molecule. You can even go further and say, well, I don't really care about these 3 sites. They are close together. I want to represent this as a single site, make my computational at least 3 times faster, more normally, and I represent this by 1 site. Okay, this is kind of extreme coarse graining. I will show you the models we are using are actually of this type, right? So you represent 3 or more atoms as a single bead. So the answer is, which one is correct? There is no right answer. The right answer depends on the problem you're trying to solve. The same is true about electrostatics, right? So do we need to use charges, or is Lennard-Jones enough, right? And you might say, well, okay, depends on the polarity, of course, right? So for methane, you can say, well, you don't have to use charges, right? It's pretty much neutral. And with nitrogen, probably you can get away without, but it improves a little bit when you add charges. Carbon dioxide, I would say probably at this stage you do need to have charges because it's strongly quadrupolar. And then for water, it's obvious that you need to use charges, okay? As I showed you in the previous slide. However, do you really need to use charges, right? In the model that we are using for the self-assembly, actually water is this, okay? So, yeah, do we lose information? Absolutely. Right? Is it real water? No, no way. Is it good enough? Yes, for the problem we're trying to solve. It is impossible to solve the problems we're trying to solve by using an atomistic model of water. No way. Okay? In fact, we saw a talk by Zoli yesterday where he wasn't even using water. It was an implicit model, right? So you implicitly describe the behavior of water through some fields in your simulation, and you get rid of it altogether. So again, it's a modeling choice, just like any other. And finally, you can also choose whether you use bonded potentials or not, right? So we tend to use a lot rigid potential models. They're much faster because we don't really care about the vibrations. But if you're simulating, for example, a spectroscopy profile or something like that, then you need to use flexibility. So again, it depends on the question you're trying to answer. So just a summary of this, let's say, flexible simple point charge model for water. Okay, we build this. So when we build a model, we make assumptions. And all of these assumptions are questionable. You can say, well, no, I prefer to do this or that, okay? So we first define that there are 3 atoms. Sure, okay, that's fine. But in fact, there are many models in which we introduce a 4th site or even a 5th site, okay? These are not real atoms, but they are important sites for representing the true electrostatic potential around the molecule, okay? Like TIP4P, for example, is a 4-site model. Water has 3 atoms, not 4. Okay? But this is a better model because it represents the electrostatic potential better. But it's more expensive. Okay? 4 sites instead of 3. So it's always a balance, right? This balance is always present, right? Do we need to introduce that complexity? If yes, we do. If not, we shouldn't. Okay, so two types of site. The two hydrogen atoms are equivalent. You need to be able to flip the molecule symmetrically. Then this is the first big assumption, right? Include one Lennard-Jones site on the oxygen atom, okay? Not on the hydrogens. Okay, we could. There are models that include Lennard-Jones interactions on the hydrogens. And people have tried to argue that that improves the description, okay? So it's an open question. Include 1 point charge on each atom, but total molecular charge is 0. Again, it doesn't have to be on the atoms. It can be displaced. You can have more than 3 or 4 charge sites. You connect the atoms by covalent bonds, right? But of course, there's only one type of bond, OH. Also one type of angle, HOH. And this is, again, another modeling choice, right? Many models, like the typical SPC model, is rigid, right? There is no flexible bonds or angles. You can choose to do it or not. So if you make these choices, these particular choices, that leaves you with a set of parameters, right? So in this case, the flexible SPC model has 7 free parameters. Epsilon and sigma for the oxygen, not hydrogen. The charge on the oxygen, because once you fix that, then you know what the charges on the hydrogens need to be. They are constrained by the electron neutrality equation. And then the bonded potentials, the distance and force constants for the bond and the angle. For the flexible one, for the rigid one, you get rid of the k's, right? The k's are infinite effectively, so you get 5 parameters. So how do you fit that? Typically to match experimental data, or you can try to derive them from higher level of theory like quantum mechanics and fix those parameters, right? So again, we don't really cover that in this talk, but essentially the message I want to get across is that the design of a model is a balance between accuracy and computational expense. That's always present. And also, in terms of the number of parameters, like I said, right, you have to try to use the simplest model possible, but not simpler. Okay, so now on to coarse graining, right? So I told you that depending on the type of model, we can access different length and time scales. So this is a kind of simple schematic I borrowed from a paper. You see the length scale here and the time scale there, and typically the more kind of deeper level of theory models will be here, right? DFT quantum calculations will solve problems for individual molecules or small aggregates of molecules, etc., at a very accurate high level. But then you cannot do, large liquids, right? Simulations. Maybe you can now, but okay. And so you have to simplify. If you want to go here, you have to simplify. So now we go from quantum description to classical description, right? So classical description ignores electrons, etc., and so it takes into account, it assumes that everything is classical. So you can now access longer times and length scales. And then you can keep doing that, and that's what I'm going to talk about next, is this coarse-grained MD, which still retains a discrete representation of reality. So all molecules and atoms, etc., are discrete. But they're much more simplified, so we can access much larger time and length scales. You can keep doing that. My knowledge stops here, right? But we've already heard talks about higher level, like Brownian dynamics, or I missed the word now. Even continuum models, right? So when you abandon or start abandoning the continuous description of the discrete description of reality, you can get hybrid models which mix discrete and continuum, and then all the way to fully continuum models, okay? I'm not going to talk about this. I'm going to stop at the coarse-grained MD level. So there are essentially 2 ways. Let me go back to the previous slide just to say that there are essentially 2 ways of doing coarse graining, right? In fact, there are 3, as I will explain, but 2 conceptually different ones. One is bottom-up, and the other one is top-down. So bottom-up, the principle is you start from down here with a very high level description, and you simplify progressively your system. So keeping every time you simplify, you make sure that you describe the correct physics from the higher level theory as you go up the ladder. Okay, so that's bottom-up coarse graining. You can also do top-down coarse graining, which is, okay, well, I'm really trying to describe an experimental system. Sure, I can fit my parameters of an atomistic model to the experimental system, but also I can fit the parameters of a coarse-grained model to the experimental system. So we're always trying to match the experiment. That is top-down, okay? And then there's also a hybrid way which combines the 2, and that's what essentially we are using. So bottom-up, these are just some examples. Again, I'm not particularly an expert in bottom-up coarse graining. I know a little bit about these approaches, but they have been developed by many different groups. So essentially, you start from a higher level resolution. You can start from quantum mechanics. There's been work done that way, but usually you start from an atomistic description, and then you coarse grain it to a higher level using this, or to a lower level of theory using this approach. So it is the advantage is it's based on rigorous statistical mechanical theorems, right? So you can derive statistical mechanical equations that show you that there is a unique way of mapping from a higher level to a lower level, right? Depending on your target properties. And depending on the target properties, you have different flavors of this bottom-up coarse graining. So you can do Boltzmann inversion, essentially fitting the structure factors or the RDFs from your atomistic to the coarse grained. You can do force matching, which is essentially trying to match the forces between the atoms in the coarse grain and the atomistic, or you can minimize the relative entropy between the two different models. Depending on which way you choose, you will get different answers for your coarse grain model. Okay? There's a debate about which one of these approaches is best. I'm not going to comment on that. But the main advantage is that once you do that, because it's based on rigorous statistical mechanics, then it has the potential to be predictive. Okay? So you don't need experimental data to anchor your system. You are just essentially going up the ladder and making the model simpler, but trying to do predictions of what is going to happen in experiment. The downside, of course, is that precisely because you don't have those anchors, then if you move away from the conditions in which you parameterize your model, it can no longer work, okay? Or it may fail. And I've, in fact, experienced this with, I had a postdoc for a while trying to do inverse Monte Carlo of a surfactant system, and the model we got depended on which data we used to derive the coarse grained. Okay? So if we tried to fit a micellar system, we would get a micellar system. We could do predictions in the micellar region, but then it wouldn't predict the liquid crystals at a later, higher concentration, and vice versa. Okay? I'll show you some graphs where that is more evident. And so this is just a schematic depiction. You start with an atomistic description, and then you fit, in this case, the RDF, so you would be doing Boltzmann inversion or inverse Monte Carlo, and that coarse grain model is the best fit to that representation, and that gives you then an ability to run larger simulations using this. So top-down is the opposite approach, right? We abandon any knowledge of a higher level model, right? We assume that we don't have it. We just try to develop the simplest representation of the experimental physics that we are seeing. There are essentially two approaches. One you can call generic or toy models, right? This is very widely used by physicists, for example, to try to understand physical phenomena in a very simple and relatable way. They are good to represent general physical principles, but then it's difficult to translate that to specific experimental systems, as you would expect. Or you can use a fit to a subset of experimental properties, and they're what we would call the chemically specific models, but then they lose transferability when you move away from that fit. So essentially, they do not require or imply the existence of a higher resolution model. The downside is that they tend to be less rigorous because they're not based on principles, and they're generally under constraint. So it's non-unique, right? It depends on which way you parameterize, you get completely different approaches. So this is just another example from Athanasios Panagiotopoulos' work. So this is describing, again, a surfactant system, a micelle formation, using this very simple lattice model of surfactants. So you can see how simplified you can get and still represent the basic physics in the system, okay? So this is based on no atomistic description whatsoever. Okay, and this is the approach we are using. We are using a bit of both, okay? So we are based on something called the Martini model, which is originally a top-down approach, but it has become more and more bottom-up as the model has been developed. And our approach for deriving this model is very much hybrid, right? What I mean by hybrid is that you do start with a higher level of theory. We started, in fact, from quantum calculations to determine parameters for an atomistic model, and then use the atomistic model to validate increasingly coarse-grained models. But at every step of the way, we also do a kind of sanity check against experiments, okay? So for example, I'll show you that in some cases we use the atomistic model to validate the surfactant description, and then we use the silica model or we use the data on silica to validate the mesoscale model, etc., etc. Okay? So what this means is that what we are trying to do is to develop a more simplified description of the system, but that still captures the basic physics that we are interested in. okay? And that still represents a realistic experimental system. So we can tell experimentalists then that, yes, we are synthesizing silica at this concentration, this pH, this temperature, right? So it's directly mappable to experiment, okay? Okay, so that's the end of kind of the pedagogic part of the talk, right? So this is about modeling and coarse graining, and now I'm going to go into the materials that we are actually trying to synthesize. So this research, as Desho mentioned at the start, is about nanoporous material design. And so what we're trying to do, in the kind of research vision of the group, is to try to establish links between synthesis parameters, so what I informally call the soup, right, where experimentalists mix ingredients and shake them and heat it, and then at the end you get a material, right? That's where my knowledge of the process ends, right? Yeah, it's a soup. So you put the material of the soup in, and you change the conditions, and you get different materials at the end, right? And so what we're trying to do is to establish relationships between the synthesis of conditions and the structure and properties of the material. And then once we know what the material looks like, then we also establish theoretical relationships between the structure and properties and the performance of the material. And that's where the adsorption that Desho mentioned comes in, right? I'm not going to actually talk about this step. This is a different area of research where we try to predict the behavior of material for adsorption, gas separation, etc., based on knowledge of the structure and properties of the solid. What I'm going to talk about today is the first step. Can we relate synthesis conditions to structure and properties? So for that, actually, it is quite challenging to do, and so we need to use very large length and time scales, and so coarse-grained models. So this is the prototypical material we're looking at. We've looked at, as you'll see during the talk, at variations of this kind of material. So they are formed by silica walls. They're typically amorphous. This looks a bit crystalline, but it's not. They're amorphous silica walls, but they are ordered on the mesoscale. So these pores are ordered in this case hexagonally, but they can also be ordered lamellary or cubically or etc. Right? So there's mesoscale order, but not atomistic level order. So this kind of order is enforced by interactions between a surfactant template, right? So the surfactant is what forms these kind of micelle arrangements, and they interact with the silica around it, and that's what generates these mesoscale structures. Okay? Now, no one really knew how that happened, and so we're trying to generate some models to get some insight into this, and then use it to make predictions about this kind of system. So, of course, the challenge is that there's a lot happening at the same time. So the self-assembly of the surfactant, right, which I'll talk about in a second. There's reactions, chemical reactions, condensation of the silica in the solution as well. There's phase transition, so there's phase separation between dilute and the concentrated phase, etc. There's nucleation of the silica material, etc. Everything is happening at the same time. Of course, we cannot represent everything, but what we need to do in the model is try to retain the key physics and simplify all the rest. So, going through the ladder, right, of how we developed this model. So we started by doing quantum calculations on small silicate molecules. So there was no atomistic model of silica when we started this work. Okay? And the main reason is because experimentally these silica species don't really exist. They're transient, right? So they react very quickly and polymerize and form a gel, and so you can't really measure their properties. So we started with quantum calculations, used that to develop models or parameters for an atomistic model of silica. And this was the first model of silica published, I think, as far as I'm aware. And then we combined that with, of course, water, counterions, and a surfactant. So the typical surfactant for these materials is an ammonium surfactant, which has a positively charged head and a hydrophobic tail. Okay? And the length of the tail is also important because it gives rise to different pore sizes. So these surfactants tend to aggregate. They're amphiphilic, right? And for those who don't know what that means, it means that there's a balance between these interactions. So this part, the charged part of the surfactant wants to interact with water. The non-polar part doesn't, and so you give rise to this kind of frustrated, in a way, arrangements of these surfactants. For example, micelles or liquid crystals, etc. So then the next step is, okay, we have the atomistic model, we validated it, etc. And now we need to coarse grain it. So the way we do it is we lump together a set of atoms, right? So for example, these 4 tail atoms turn into a bead, the head atoms turn into another different bead, etc. And then you describe them using a coarse grain model. So these interactions are now very effective. right? So they lump together a lot of the physics in the system, but you can still see that you're still representing your surfactant as something that is amphiphilic, right? You have a polar head and then, you know, an apolar tail, okay? And we developed, again, this new coarse-grained model for silica monomers, which can then also polymerize and form oligomers and so on. Okay, so this is an example of a validation step where we look at the pure coarse-grained surfactant water solutions. This is the experimental phase diagram, right? So what happens in these kind of self-assembly systems is when you have a very dilute solution, the surfactant is dissolved in the water, so they're just monomers floating around. And then you hit a threshold, which is called the critical micelle concentration, right? At that point, the surfactant, essentially it's almost like you can think of it as a solubility limit, right? The surfactants are no longer happy on their own, they need to aggregate, right? There's those non-polar domains start to aggregate together and they form micelles, right? So these micelles are reproduced by the computational model, and in fact, as I'll show you in the next slide, they match experimental data for this. As you increase the concentration, you change the curvature of these systems, right? So if you have too many surfactants, the micelles are no longer stable, they merge and they form these elongated worm-like micelles, right? Which we can also reproduce. And then as you keep increasing the concentration, remember this is all without silica, then you can form these hexagonal liquid crystals. So these are now dominated by surfactants, more than 50% weight. You get hexagonal phase here, and you can get a lamellar phase here, and then in the middle you get a bicontinuous cubic phase as well, okay? And our model is able to reproduce all of that for the surfactant. Now, one thing before I move forward is that in the materials I showed you before, that also form hexagonal phases and lamellar phases, etc. Those are all done experimentally in this regime of micellar phase, okay? So it's not the self-assembly is not caused by increasing surfactant concentration, but by adding silica into the system. So keep that in mind as we go along, because I'll show you what the effect of silica is. Before I do that, let me show you the quantitative validation against experimental data. So this is trying to reproduce the aggregation number of the surfactant as a function of concentration of surfactant. And you can see that our simulation points overlap on the experimental trend pretty well, even though this is a very, very simplified model. Okay? So this is just an example of this kind of validation. So we can validate against the higher level of theory and against experiment at every step of the way. So this is a validation against a higher level of theory, right? So now we have silica in the system, we simulate a single micelle, and we look at the density profile to see where the silica is and whether that compares well with the atomistic level. And you can see that the coarse grain reproduces the atomistic description in a good way, okay? Okay, so what happens in the system? I'm going to have to move faster, I think. I overestimated the time. So when you add silica to the system, the first thing that happens is you start from a micellar distribution and you get elongation of micelles. So why does this happen? The silica is negatively charged. This synthesis takes place at high pH. So surfactant is always positively charged. The silica is negatively charged, right? That creates a counter-ion effect. So the silica absorbs very, very closely to the surfactant. It's very strongly absorbing. And this absorption at the surfactant interface screens the repulsion between the positively charged head groups. So the head groups repel less, which means that you can decrease the curvature, right? So let me think of it a different way, right? So you have a surfactant, and you have a neighboring surfactant and a repulsive positive interaction at the surface. That means that within that micellar aggregate, the surfactant heads will try to be as far apart as possible, but not further apart, because they are constrained by the volume of the hydrophobic region, okay? So that essentially that balance between the hydrophobic volume and the hydrophilic area per head group dictates the curvature of your aggregate. If you now add a counter-ion to it, right, it diffuses or it screens the repulsion between the head groups, so they can now come closer together, mediated by the counter-ion. So you reduce the area per head group, you decrease the curvature. That allows you to form these elongated micelles, whereas without silica, it would be a spherical aggregate, right? So you're reducing the curvature. So then we showed that actually under experimental conditions, this is a landmark kind of benchmark paper of these materials where they looked at the detailed silica speciation. So we used that experimental information to map it into a coarse grain model, and we showed that under those conditions, exactly the same structures as predicted or as shown experimentally were predicted, namely these hexagonal mesophases. Okay, so this was the first time that any model was able to predict the formation of this kind of structure in the computer. Okay. So, as you might be thinking, right? Sorry, I'm just going to go back. So, with silica monomers, you only form these elongated micelles, but I haven't explained to you how we go from that to these aggregated hexagonal liquid crystals. And the answer is you let the silica polymerize. So when you add monomers, it goes into worm-like micelles. But if you now let the silica form dimers, which happens in the reaction as you go along, right? The silica polymerizes and starts to aggregate. Then those dimers actually promote intermicelle aggregation, right? Let me show you the next slide. I think I have the... no, actually I don't. So the way this works is, again, now we have still this screening of the attractions, right, of the repulsions of the head group, so you have lower curvature. But crucially, now we have two negative charges bonded together. So you have a multi-charged counterion. That essentially forms a bridge between adjacent micelles. So one side of the counterion is attracted to one micelle, the other one to the other micelle, and it allows them to aggregate together. Whereas if they didn't have that, they would be repelled. Okay? And so that actually allows you to transition from these worm-like micelles into these hexagonal liquid crystals. And we've shown that this is reversible, so it's equilibrium transition. Okay? So that helps us to explain, again, how we can go from a micellar system by adding silica through a cooperative process into these hexagonal liquid crystals. So we were able to trace essentially the whole mechanism of this material synthesis from the start until the end of the material formation. So very briefly, we can then play around with this, right, which we cannot do experimentally, but we can do computationally. So we can isolate variables. That's the advantage of doing computations. So we can ask, how does silica condensation affect mesostructure? So we can start with dimers. That gives you hexagonal phase. You can keep the silica concentration constant, but now condense these into tetramers and then to an octamer, right? So everything is kept the same. You just condense the silica. And you see that that actually leads to another change in curvature. So we are concentrating the charge. These are much more charge dense, these octamers, right? So the density of charge allows you to even lower the curvature further and transition to a lamellar phase, okay? So again, we're trying to explain how we transition to these phases based on simple physical understanding of what's going on. We can show the same with the degree of charge. So we can go from, we can keep now the speciation constant, but we protonate or deprotonate. So this would, in a way, represent a change in pH of the solution, right? So as you change that, again, you change the degree of charge. That changes the curvature of the aggregates, and you can go back to hexagonal phase at lower charge, okay? We can also add a co-solvent, right? So essentially by doing this, we are now filling the volume. So now we're not playing with the repulsive surface of the micelles. We are now playing with the volume of the hydrophobic region, right? So we can fill in that volume by adding something non-polar like benzene, and that goes to lamellar phase. And then if you remove the benzene, it goes back to hexagonal. And that's exactly what experimentalists see by using these co-solvents, okay? And then just we showed that we can actually reproduce the whole family of these periodic mesoporous materials at different conditions that match experiment. So I'm probably running out of time. Do I have 5 minutes, Desha, maybe? Or? Sure. Okay, so I will skip all of this. We've looked at other materials like hybrid organic and inorganic materials. And now, more recently, we've been looking at bio-inspired materials, so trying to emulate biosilicification, which happens in nature, using our models to try to understand how this process goes about, and trying to produce more environmentally friendly silica materials. But in the interest of time, I will skip that. And then I just want to tell you a bit about this reactive model. Okay, so this will be the final bit. So all of the simulations that I showed you before, right, pre-assume a given silica condensation rate. Okay, so let me show you. So you can represent this, the experimental progression, or the progression of the experimental synthesis, on this kind of diagram, where you have the self-assembly on the horizontal axis and the silica polymerization or the condensation of the silicates on a vertical axis. Okay? So in experiment, these are more or less happening at the same time. In the simulations, however, we do it in steps. So as I showed you, we start by self-assembling the surfactant without silica. That's the first step of the simulation, the reaction. Then if we want to introduce silica, we add silica to the system, right? So we introduce the monomers into our simulation and run it again. And that leads to the worm-like micelles I showed you before. Now, if we want to simulate the effect of silica condensation on this, what we do is we remove the monomers, we load dimers onto the solution, and we run the simulation again. Okay? And that's how we got the hexagonal phase. And this is because, of course, our model is not reactive. It cannot simulate a reaction on the fly. And as I told you, experimentally, that's not the case, right? The reaction, the self-assembly can progress simultaneously. Now, for these materials that I showed you before, the reaction is actually much faster. Sorry, yes, the reaction is much faster than or much slower than the self-assembly, right? So which means that we can self-assemble, assuming no reaction takes place, and then jump to a later stage where the reaction has taken place, self-assemble again, and so on. And that is a good representation of the actual case. Now, with the bio-inspired silica that we were working on recently, that's not the case. The reaction is much faster, and so we actually now need a model that can represent the reaction and the self-assembly at the same time. Okay? And so we've developed this called reactive coarse grain model. So we are going from the previous work from atomistic to non-reactive coarse graining, and now we're going to reactive coarse grain. So we have to devise a framework that allows us to connect dimers, to connect monomers into oligomers, and then also break them, because this reaction is reversible in practice. Okay? So, you know, we had a student working on this, André, for several years, essentially his whole PhD, and he managed to come up with this rather ingenious approach where we add sticky particles. So this is the silica monomer, the gray sphere, and then we add sticky particles at the 4 tetrahedral positions of oxygens where the reaction is likely to take place. And then we counteract that with repulsive virtual sites to prevent non-tetrahedral arrangements from occurring, because they don't occur experimentally, and also to keep the reaction order, the coordination number, in check, right? So we want to have maximum 4 coordination number, not more than that. And so he's adjusted the parameters to match experimental data on the silica condensation rate with over time, and we get good agreement. And then that allows us to simulate the reaction in real time. And this is just an example following 2 silica monomers during the reaction over time. You can see that they are separated here initially, they fluctuate, their positions, etc. And then when they come into close contact at the right orientation, they form a bond. Okay? And the bond is purely physical, there's nothing chemical about it, it's just a very strong Lennard-Jones interaction, right? And then they essentially diffuse as a dimer, right, during this period. So much less, so the distance is more or less constant. And then at some point, they get a kick from someone else, right, and they break, okay? And they break and they go about and do something else, okay? So they are separated. So this demonstrates that we are able to describe a reversible reaction, and the kinetics are similar to experiment because they match the experimental kinetic data that I showed you before, okay? And so using that, we are now able to simulate self-assembly and reaction at the same time. And this example is an example of micelle encapsulation, as a very simplified process where you form a micelle from solution, and that micelle is coated by a layer of silica. Okay? So we start with a random distribution of monomers and silicates, surfactants and silicates, and then the surfactants start to aggregate, and you can already see at this stage that, well, you can't because it's very small, but you can trust me that you can see aggregates of silica forming already in the solution at this stage, and in fact, in particular, close to the surfactant interface. So then these micelles grow, etc., and then you reach a point where you have protomicelles that are almost completely covered in silica. And I thought, okay, this is going to be the limit. It's not going to progress further than this because they are essentially frozen by the silica shell. But in reality, it's not, and that just shows that the reversibility of the silica reaction is key to this encapsulation process, because what happened was that as the micelles approached, the silica was able to open and accommodate the fusion of the 2 micelles. We followed that in real time, and it was really neat to see. And then eventually you form a single micelle, which is now coated with a nice layer of silica. Okay? And just to show you that that's the case, so this is the kind of structure you can form. This is a hexamer of silica around at surfactant head group. And here you can see if I cut it, this is the layer of silica around the micelle. And you can see that it's kind of hollow, right? So the inside is surfactant. So this would be what would happen if you then burned off the surfactant in calcination afterwards. Okay, you get a silica shell, right? So this is kind of reminiscent of silica nanoparticle synthesis as well experimentally. Okay, so hopefully that's the end of it. So hopefully I was able to teach you something new about modeling, in particular coarse graining, and how basically the main take-home message is every model is a compromise, right? Every model makes assumptions, and you should not take that for granted. You should always think about how you validate the model, how you improve it, etc., and whether it's the right model to answer the questions you're trying to answer, okay? And then apply that to self-assembly and solution, in particular in the synthesis of silica materials, and show you how these different physical variables can change the way the system evolves in time and can change the morphology and the structure of your materials. So, of course, this work was not done primarily by me. It was done by a lot of very clever people working with me over the years. In particular, the work I've showed here was the first mesoscale model was developed by Germain while I was still in Portugal. The bio-inspired work was then followed on by Alessia and Tom more recently, who just graduated. So thank you to the funders, and thank you all for your attention. Happy to answer any questions.
Thank you very much, Miguel, for this eye-opening talk about self-assembly and, let's call it, intelligent modeling.
Your words, not mine.
The floor is open for questions. Come in.
Thank you. So, very impressive work, Miguel. So I was wondering about, so I have a question to the reactive, non-reactive models. So maybe I missed it, but how do you exchange your monomers to dimers in the reactive model?
In the non-reactive model?
Yeah.
Oh, you do it by hand, right? So you take the final configuration of the monomer simulation, right? You remove all the monomers, so you delete them from the trajectory, right, or from the configuration file. Mm-hmm. Then you resolvate the aggregates. So you keep the aggregates in place, you resolvate, you first add the dimers into the solution space, then you resolvate, and then you let it run.
So you don't replace them one by one?
No, you don't replace them one by one. You could do that, right? We thought about doing that. You could do that, for example, with a kind of hybrid MD Monte Carlo step, and that's possible to do. But then we try to go to the reactive way instead of doing that. That would probably be a bit more realistic. So the problem, of course, is that you really don't have information about the chemical potential of these species. Yeah. So you cannot really develop a robust acceptance trial for removing or replacing a dimer with a monomer, right? Yeah, you can guess, but it's not going to be very, very realistic.
And in the reactive model, so what is the interaction between the patches? So how do you?
So the sticky particles interact with other sticky particles through a very strong Lennard-Jones potential, because it's still based on the Martini, which is Lennard-Jones based. So they interact very strongly at very short distances. So it has a short cutoff and a very deep well. So when they come into close contact, they will attract, and if they're far apart, they won't. Now, if you just do that, then you will have essentially, you can have up to number 8 or 9 coordination, because you can just fill or surround the central monomer with other monomers. So in order to keep that coordination number at 4, and keep the tetrahedral orientation of the silica, we had to put those virtual patches, which are essentially repulsive. Let me show you the potential map, which I had to skip over. Right. So this is the potential map here. You see that it's a cut, right? So this is the plane of this sticky particle, and you see that in this plane, the only point at which it can react is really in the vicinity of that sticky particle. And once one monomer attracts there, then you don't have any well. The other monomers don't feel the well because they're too far away, right? And they're drowned by this virtual site repulsive interaction here, okay? And of course, if you cut in any other plane with the tetrahedral, you'll see that's also the case.
And you fit, last question, you fit the parameters to match the association, dissociation?
The kinetics, yeah.
Okay, thanks.
So one thing I would add also to this is that this is highly coarse-grained as well. There is no information about reaction kinetics other than fitting to experimental profiles, right? So we don't have any activation barriers. We don't really describe the intermediate species or anything like that. It's just a purely kind of heuristic bond between the two sites.
Canonical scheme would have been my question, but you shut it down.
I mean, I'm not shutting it down. It's certainly possible. We just didn't go that way.
Okay, thank you very much. It was very, very nice talk. And my question is concerning what is important for listening to the youngest one. You remark about the force field matching procedure, and nowadays there is a tremendous article in which published if your potential based on some machine learning based force field using some DFT or CCA or high-level ab initio quantum chemistry is practically something which describes the nature. What is your feeling about this?
Yeah, I mean, that's an interesting philosophical discussion that we could probably spend an hour on. Maybe later after the political discussion we can discuss this. I mean, honestly, I think there's a lot of potential in these machine learning potentials, right? I think the basic philosophy is that you describe the quantum chemistry, you access longer time and length scales at quantum level accuracy, right? Okay, that's fine. But of course, the model is only as good as the quantum data that you use to fit it. So if the quantum model already has approximations and flaws, those will amplify in the machine learning. If you can do, for example, we were discussing yesterday, coupled cluster machine learning potential, right? I mean, in principle, those would be accurate. But then there's also the question about the breadth, right? So, okay, you can describe water by fitting the pure liquid, but then you put it in the vicinity of a protein, and it doesn't behave like water anymore because those data were not used to fit. That's, I think, my concern. I mean, things are getting better and people are improving, very clever people working on improving these things. So in the future, I think we will see a bigger role for this kind of model. At the moment, I mean, maybe I'm old-fashioned, but I still prefer kind of the physics-based simplification as you go along, and that's been the approach we've used.
All right, any more questions? In that case, I would like to thank Miguel for this great talk.
Thank you.
Okay, České Budějovice is a nice town in South Bohemia, and it's famous for two things. One is Švejk. Who is it who read the Švejk from Jaroslav Hašek? If you didn't do so, please do so. It's great. It's about the absurdity of war, and it's becoming more and more relevant in this age. Okay, the other person about whom České Budějovice is famous is Milan Predota. Our next speaker, who's working at the University of South Bohemia in České Budějovice, and he's going to talk about molecules in motion, electrokinetic phenomena. So he's going to talk about everything, which is the basic topic of this conference. Milan, the floor is yours.
Thank you. I'm grateful to the organizing committee to giving me the opportunity to speak here. Of course, I will not talk about everything about molecules in motion, but I will focus on the electrokinetic phenomena, which I find a fascinating application and fascinating case of molecular motion. I will start with a more general introduction because there are both equilibrium and non-equilibrium molecular dynamics approaches to see motion or in general any transport. So I will first introduce that, and then I will present our simulations of electroosmosis which led to the simulation determination of zeta potential. I will explain why it's important, and I will end up with the current research, which also uses electrokinetic phenomena, and that's capacitive deionization in graphene nanopores. So I will start directly with giving you examples of the electrokinetic phenomena and their application. And one of the electrokinetic, it's a family of closely related phenomena. And let's start with electrophoresis. In electrophoresis, you have a charged ion, or rather charged colloidal particle, and it can be micrometer sized. And if you apply a DC voltage between two electrodes, the particle, of course, will start to move, and you can observe the speed. There will be constant speed proportional to the size of the electric field, and the ratio gives you the electrophoretic mobility. So in this case, it's electric field which is applied. It's the velocity which is observed, and this is true even for the electroosmosis. And in this case, it's the solid phase which is moving with respect to basically immobile surrounding liquid. And the last thing is reversed if we do electroosmosis. In this case, you have solid surface. It can be a cylindrical capillary. It can be some planar space sheet. And again, the surfaces will be charged. And then there will be some counter ions in the aqueous solution. And you apply electric field from left to right, like between the two ends of the capillary, and it will cause a motion of the liquid. So the whole liquid and the whole volume of the pore will move in the direction depending on the surface charge and the electric field. So in this case, the solid phase is immobile, and it's the liquid phase that's immobile, but still it's electric field induced, and you observe the velocity. And there is this bottom row, which again, it's still about relative motion of oppositely charged phases. If you have a colloidal solution, the particles can sediment just due to gravitation, and you have a charged colloidal particles which sediment. Some charge will be very closely moving with the particle, and some part of the charge will be a bit mobile, will be a bit lagged behind the motion of those particles. So if you just let it sediment, so the particles will move top to bottom in your vessel, it will generate a difference in electrostatic potential top to bottom, and you can measure either the sedimentation potential or current top to bottom. So in this case, no electricity applied, but rather it's generated, and it's measured. So, and finally, like the analog of electroosmosis, if you have again this charged capillary, and you just force the liquid to flow, some plug flow, pressure gradient, simply non-electrostatically forced motion, you will again strip part of the charge to move, and that will generate again a DC difference or electric current, like left to right along the capillary, and that again can be measured. So basically these are the four phenomena, but the theory is unified for all of these processes. And you can say, okay, so I was talking that we have a motion of charged particles, but in fact many molecules are neutral, many surfaces are uncharged. So is it really so common to have some charged particle moving in between surfaces or in electric field? And I would say that yes, many molecules are neutral in vacuum. But if you insert them to a solution, and if there is some charge transfer between the molecule and the solvent, typically there will be some exchange of charge, and the molecules will become charged just due to interaction with the solvent. And particularly in the case of water, which has pH and some concentration of hydronium and hydroxyl ions, it's very common that molecules, particularly organic molecules which have oxygen and hydrogen, will become charged. So let's say here we have a molecule at the pH when it's really neutral. So here we have missing hydrogen from the carboxylic group, but here we have extra hydrogen on this amino group. And if then you lower the pH, so there will be a surplus of H plus ions in the solution. They will simply react with the molecule, and the molecule will become positively charged. And the opposite, of course, happens at the high pH when there is a surplus of OH minus groups, and you are losing one hydrogen. And depending, of course, on the pK, etc., simply you have negatively charged molecules. So basically, both molecules as well as surfaces easily become charged, and the pH value where the molecules or surfaces are neutral is not the pH 7, but it's a specific material or molecule-specific pH value, which is called the isoelectric point or point of zero charge. And it really can vary. For titanium, which I will simulate, it's like 5.4. For quartz, the pH when it's uncharged is about only 3, so it's really material specific. So this is just to stress, charged colloidal particles are in fact a very common thing. And so if we talk about motion of ions, maybe one of the first application you might think of course, will be something related to batteries, energy storage. And in fact, this is really a very important application, particularly nowadays when we have batteries which include polymers, and really the motion of ions and complex ions in these complex electrodes is definitely not trivial to explore. So definitely that's a big application, and things are much more complex in these polymer based batteries than in the old school sulfur, lead sulfur batteries. The opposite process can be something like if you apply the electricity, you can do electrolysis, or you can use it to do electrophoretic deposition. So in this case, you carry the particles from one electrode to the other, and the material adsorbs on the electrode. So it can be really as simple as the old school electrolysis, but also you can use some ions as carriers, like for example these clay nanotubes. And for example, in this application, it's for titanium, basically implants. If you want to improve the healing of the implantation of the artificial joint, you can deposit in the titanium material also some basic antibiotics or some organic substance which prevents inflammation, etc. And as you already know, if you choose proper pH for this process, you will have even the biomolecule charged. It will somehow stick to this carrier, and you can electrodeposit even organic material to this titanium alloy. Big application of electrokinetic phenomena is electrophoresis. It's absolutely standard technique for the biologists who use it to determine the molecular weight of different substances. And it's particularly used for DNA because, as we have learned yesterday, DNA is charged due to the phosphate groups, so it's negatively charged. So of course it will be very ready to be transformed through very narrow capillary between two electrodes. And particularly if you use some enzymatic chopper to split your DNA into chunks, you can even do full sequencing of the DNA and really see what's the series of your amino acids in the DNA. So really biologists use either this simplified electrophoresis where you just see the layers of substances with a different molecular weight, or the even modern sequences. That's really a very common application. Also, more and more, we want to have some quick analysis in medicine or biology, like, for example, to measure your glucose level, etc. And those devices can also profit from electrokinetics because it's a nice method how to separate something based on its charge, and the charge depends on the biological interactions, etc. So so-called lab-on-chip devices are more and more common. Here is another picture which shows just some nano mixing using alternating current to perfectly mix your substance. Also, this picture shows that nowadays it's possible to basically manipulate using electric field the molecules and really selectively transfer one molecule from one place to another and do whatever analysis or reactions on the nano side. Even another case of using electrokinetic processes together with other electrochemical processes is, for example, the quick testing of viruses, because in this case, of course, you don't want to do sequences if you want to analyze 10 million people, right? But you need something which is cheaper, and you can really use, again, the electrokinetic phenomena to transport the virus and at the electrode, and from that signal you can get with some high probability answer if it's the virus you are interested in or not. Water and wastewater treatment, again, something which can mix electrokinetic phenomena with standard adsorption, desorption, coagulation, sedimentation, etc. I'm not saying that all these processes are only electrokinetics, but electrokinetics can be part of it, which can, for example, transport the material or separate it. And as I mentioned, I will end up this talk with applications in desalination technologies. And also soil remediation can use nanoparticles and augmented with electric currents to basically the particles are pumped to the contaminated soil. The particular heavy ions adsorb on those nanoparticles, and then on the surface the nanoparticles can be cleaned, reused, and the contaminant collected. And maybe even 20, 30 years ago, even the people who are not scientists knew about one application of electrokinetic phenomena, and that's electroosmotic dehumidifying. That means that there were electrodes which were drilled to old buildings, and voltage was applied to these electrodes, and it helped really to move the water up and dry the buildings. By the way, the first picture I got when searching for this was from dehumidifying the Astronomical Institute of the Czech Academy of Sciences. And while at old times you really had to drill at each like 2 meters the wall to put the electrode, which is a terrible work, particularly in stone buildings. So this new version uses basically wireless electric field, and so of course wireless has a lot of advantages, at least for some. So let's, after this introduction, let's introduce the topic of transport phenomena. And always, if you have some gradient, it causes some flow, some transfer of some property. And I will start with, if you have a gradient of temperature, then it generates the heat flow, and the ratio between these two properties, that's the heat conductivity. If you have a gradient of concentration between two places, you have a mass transport. The particles move from one location to the other, and the proportionality constant is called the diffusivity. If you have an electric field and you apply it to solution with ions, the ions will move at some velocity, and the ratio of the velocity to the magnitude of the electric field is called the ionic mobility. But not only particles or energy can be transferred, even other properties can be transferred. And for example, you can even transfer the momentum. And if you transfer the momentum in a perpendicular direction to the motion of particles, that generates the shear stress. And the shear stress is related to the shear flow of the adjacent layers, and the proportionality constant is viscosity. So even that is an example of transport, in this case of momentum. And you can calculate these transport coefficient in several ways in simulations, and I will talk about two. One will be the non-equilibrium molecular dynamics, where you really turn on the perturbation, the external force or shear or whatever, and you observe how really your system moves subject to this perturbation. Or you can use equilibrium molecular dynamics, where this perturbation is not turned on at all, but you need the theory and analysis of your standard equilibrium simulations to calculate these transport phenomena. And as an example, which in fact is not the real transport property, but I think it nicely introduces the difference between these two approaches, like equilibrium-like and non-equilibrium-like, I will mention, let's imagine you want to calculate the heat capacity CV of your system. So maybe the most intuitive approach would be something which is in the spirit of non-equilibrium MD, which means you know that the heat capacity is the amount of heat needed to warm up your system. If it's NVT, then there is no volume work, so it's a change of internal energy. And so you might run one simulation at temperature T and average its internal energy, the potential plus kinetic. And then you may run another simulation at slightly higher temperature, get its average energy. And from this ratio, basically, you get your CV. So in principle, it requires just two simulations, and the theory is basically known, right? In reality, it's not about two simulations, because typically you have to do at least like 3 to 5 simulations to find the right delta T. Because if your delta T is too small, then this difference will be very small. This difference will be also very small, and your capacity is determined with huge statistical inaccuracy. If you use too big delta T, then of course both the numbers are statistically fine, but then your CV is not the CV at temperature T, but it's rather some average CV between these two temperatures. We know that CV is not too much sensitive to temperature, but in principle we face these problems. So typically we need to select really several delta T values, and then statistically analyzing these results, choose which time difference is the best. So that would be in the spirit of non-equilibrium MD, I mean turning on the perturbation, in this case, heating up the system. Or you can do it in the spirit of the equilibrium MD, and that would mean you just run one simulation at temperature T. Absolutely standard simulation, like if you were just averaging the energy. But you need extra theory. And if you need to derive from the statistical mechanics the formula which will tell you how to calculate this heat capacity. And in this case, it's a beautiful formula and it's easy to derive it. You need to analyze not only the average energy, but also the average square, or in other terms, the fluctuation of the energy. And in these fluctuations of the energy, the heat capacity is encoded. So it's a lovely just one simulation, and you still get the response how the system would react if you raise the temperature without, in fact, raising the temperature. And the same can be applied to the real transport properties. So for example, to calculate diffusivity, you can have this setup where you divide your system into 3 parts of your box. 2 will be so-called controlled volume. So here you will keep by Grand Canonical Monte Carlo some low concentration of your particles. And there will be another control volume where you have higher chemical potential and higher concentration. And here there will be nothing controlled, but simply the particles will spontaneously diffuse from the point of high concentration to the low concentration, and you will measure the flow per some time. And you can think about any virtual plane at which you will count the particles, how much they flow. But in fact, in reality, you even don't need to count how many particles are flowing here, because it's enough just to measure how many particles needed to be inserted here in the grand canonical steps, because you simply keep inserting particles and they keep diffusing here. And again, the same number will be the number of particles that you must remove to keep this concentration low. So you see already now the setup is quite difficult. You need to combine molecular dynamics with grand canonical Monte Carlo steps. So it's not that easy to determine diffusivity from non-equilibrium MD. But it's much easier to determine diffusivity from the equilibrium MD. Again, you just do absolutely standard simulation without any perturbation, but you need the mathematics to tell you what's this diffusivity. And this is well known that to get the diffusivity, it's enough just to monitor the mean square deviation, how much your particles diffuse over a given time, and you, of course, are averaging this over all possible time starts, and you can average it over all particles of the same kind, and you get a function of this mean square displacement as a function of time. And the theory says that it should be linear, and the slope is twice the diffusivity per coordinate, or 6D if you average the whole vector. So in this case, the equilibrium MD determination is much, much better, and even statistically much better. And at the same time, this works perfectly for bulk systems. If you have complex zeolites, etc., sometimes you need to do the non-equilibrium MD. So there is the third method, how to get these transport coefficients. I will not talk about it, and that you can also get it by integration of the, in this case, velocity autocorrelation function. The theory is well described, for example, in the Ellen Tildeslis book. So let's introduce our system. That's our system. And we would like to see what's the diffusivity not only far from the surfaces. So always the dark blue will be the cation, the rubidium, and the cyan will be the chloride counterions. And here, in this case, we will have the titanium dioxide, rutyl, which will be either positively, negatively, or neutrally charged. And we can average the diffusivity in layers based on the distance. And the graph will look like this. I said that it should be always linear, but it's linear only due to the diffusive equation. Real particles also obey deterministic Newton's equation for short times. So that's why at short times there is violation, but we can fit it in some range. And for example, this would be the mean square deviation evolution for some layer close to the surface. This would be for layer which is furthest from the surface and more mobile. And as soon as you are far from the surface, all the slopes will be basically the same. And the first layer basically is immobile, and it has a zero diffusivity. So always it's better to average over as long time as possible. But here, if you want to keep it local, it means you don't want your particle to move far away during your time of measurement. We really keep it on the level of only a few picoseconds, this tracking of the mean square deviation. So from each of these layers, from each of these curves, we got the slope, and then we can plot this slope as a function of distance, as position with respect to the surface. And here is the result. We separately analyzed the perpendicular diffusivity in the z direction and the lateral diffusivity along the surface, and you can see it has quite strange shape, but it will become clear when I add the curve which shows the density of adsorbed water. And you see there's a first layer of adsorbed water molecules with basically zero diffusivity. There's a second layer of water molecules, and there in this high density region, the diffusivity is small. Then we have a third peak, and again in the third peak, the diffusivity is smaller, particularly the perpendicular one, because it's harder to move layer to layer, while it's much easier to move within a layer. and there is an enhanced diffusivity in between the layers. So the diffusivity perfectly anti-correlates with the density, and you see that as close as, I don't know, 15 angstroms from the surface, we have a bulk-like diffusivity equal to the bulk value. And we did later the same work for ions, and in that case, again, there is a huge drop of the diffusivity. This is the same plot in semi-log, and particularly the divalent ions, they are very immobile in the last few angstroms, and that can be important for applications like hetero catalysis, when really you need molecules to come to the direct contact with the catalyst. So let's move closer to the electrokinetic phenomena. So again, if you wanted to determine mobility, you can use non-equilibrium MD, for example, turn on the force acting on, for example, one particle and measure its velocity. Or you can try to do it with equilibrium MD, and that means you need some formula which will tell you what's the mobility, ionic mobility. In this case, we are lucky because the derivation is known for long, and it leads to the called Einstein-Smoluchowski equation, which is a special case of the famous fluctuation dissipation theorem, because you can think of definitely of this mobility like dissipation, because you apply force on particle, but you don't accelerate it because it dissipates the energy to the surrounding particles. And you can think about diffusivity like Brownian motion, typical example of stochastic fluctuation kind of motion. And you can also calculate the electric conductivity, either turn on the electric field acting on all ions and calculate how many ions per second trespass some virtual plane. Or again, you can say, okay, can I calculate it directly from equilibrium MD, just monitoring something without the applied electric field? And again, the answer is yes. And again, it's only the diffusivity of each species which needs to be monitored in equilibrium MD. And if you multiply it by its charge, etc., you get the conductivity directly from EMD without turning on the electric field. But we said we are interested in the motion of colloidal particles. So let's say a few words about what's happening on the surface of colloidal particles, or solid particles in general. So let's say that you have a positively charged surface. So of course there will be a layer of typically strongly adsorbed counter ions, in this case negative ions. And then can be some diffuse layer where both cations and anions are at different concentrations. And this is called the electric double layer. And the screening, how quickly the surface charge is compensated, depends on the concentration of the salt. If you have low ionic strength, few ions to compensate it, your double layer is very thick, and the electric field extends to maybe dozens, hundreds of nanometers. If you have high ionic strength, your thickness can shrink to basically a few nanometers. So the salt concentration definitely is very important. And this distance can be approximated or expressed via the Debye length, which inversely depends on the concentration and charges of the ions. And now we are going to the motion of particles. So imagine you already have a charged particles, you apply the electric field, and the particle will move. But most particles don't move like Dejo with the naked surface. So it's not this particle surface which would be important, but in fact most particles move like PAL, covered with some layer which shields you. And that's this layer of strongly adsorbed ions. So basically, when the particle moves, it's not only this green solid surface, but it moves including this bluish layer of strongly adsorbed counter ions. And also then when the particles interact, it's not the properties here at the real solid surface, but it's rather here, the properties here, between on the immobile and mobile parts of this particle. And that's why when we characterize the interaction of colloidal particles, it's rather not the surface potential, but it's rather the electrostatic potential somewhere here at this also called slip plane, which determines the mutual interaction of particles. And the potential at this slip plane is termed the zeta potential, and it's a big and key property in colloidal chemistry. It typically has the same sign as the surface charge and the same sign as the surface potential, but it's lower because, of course, part of the electrostatic is already screened. So here you can see at low pH, typically the zeta potential is positive. And at high pH, because you have a lot of OH minus on the surface, the zeta potential is negative, and typically it's of the order of tenths of millivolts, and it's 0 at the point of 0 charge. And it's also important for the stability of colloids, because it's said that if your zeta potential in magnitude will be larger than 20 or 30, it means all your particles are significantly charged. It means the particles repel each other, and that's why the particles don't sediment. They are beautifully dispersed, and that's good if you want to do some scattering experiments or simply interact with the surface of each particle, while if the zeta potential is very small, the electrostatic is not strong enough, and van der Waals interactions can win, and then you have coagulation, sedimentation of the particles, and simply you get some big chunk of particles. So, so it's the zeta potential, and the zeta potential, which is measured in these millivolts, is calculated typically from experiments which measure only the mobility of the particles. So what's measured is the speed of the particles, v, u divided by the electric field, and that's the electrophoretic or electroosmotic mobility. And the other constants are just bulk-like viscosity of the liquid and dielectric constant. So this is the key equation which both the experimentalist as well as me use to convert the directly observed mobility to something which is being published like a property of the particle. It can be derived, by the way, this Helmholtz-Smoluchowski equation, just combining the surface electrostatics, the shear flow, the capacitor, etc., and the result doesn't depend on the location of the layer. It's the electrostatic at this layer of mobile ions. So my first approach was trying to get the zeta potential directly inspecting the electrostatic profile, because it's reported in millivolts, so somewhere at the interface we should see some point where we can read 20 millivolts, but in fact it turned absolutely impossible. The lines are shifted by 2 volts, but if you look here, you see you have oscillations of the order of 1 volt, and maybe somewhere here far from the surface you might reach the millivolts, but then you have either oscillations or continuous change, definitely no point where you would easily be able to read the zeta potential. So I decided to do directly the simulations of electrokinetic phenomena. In principle, I could do the simulations of electrophoresis, but that would mean I would have to have one huge particle, maybe made of 1,000 or 10,000 atoms, and I would be monitoring just the motion of one particle, which would be absolutely terribly huge system and terrible statistics. So it was much better to do the simulation of electroosmosis, where I have immobile surface. I can average the motion of a lot of water molecules, and I have very good statistics. So that's why I was modeling the electroosmosis. And this is the view of the interface. So I have electric field along the surface. So of course the blue cations will move in the direction of the electric field. The cyan anions will move in the opposite direction. And the highly non-trivial question is, will there be any motion of the liquid far from the surface? Will the water flow? Because of course the net electric force acting on neutral water is 0, right? So I started these simulations, and on top you can see, and now I have problems with the movies which worked when we tested it, and they don't play. So I will talk in the meanwhile. So we will have first a negatively charged surface. So the interface will be dominated by positive counter ions, and the counter ions will move in the direction to the right. Yes, thanks. And please, Jonas, now watch just at the top movie. So we have these cations, blue ones, which move to the right, and there is a majority of counter ions compensating this negative charge. And there are the anions moving in the opposite direction. What you can see is that, in fact, the water flows to the right, with the majority with the cations. And because it's electroosmosis, there is extra negative sign. So we have positive mobility, but the zeta potential is negative, and that's correct because the zeta potential should have the same sign as the surface charge. And then if we do the same for positively charged surface, you see that the interface looks very different. We have a surplus of anions, they move to the left, and they drag the water molecules with them. So we have negative mobility, and negative mobility converts to positive zeta potential, and again, that's how it should be for positively charged surfaces. So that was a good test that we can model the electroosmosis. And we can measure not only the relative motion of the liquid far from the surface, but we can even look what's the mobility of cations and anions and water as a function of distance from the interface. So very close to the surface, everything is adsorbed and immobile. Here you have this inhomogeneous region where the mobility of the ions as well as water relative to the surface builds up. And then you end up in a region which is already far from the surface, where the ions move with respect to the water with normal ionic mobility. But what's important, the whole liquid, all water, even far from the surface, moves at non-zero speed. And this is something which I find fascinating for electrotechnical phenomena, because it's a surface-induced phenomenon which affects the motion of a whole big volume. So even if you have a millimeter thick capillary, and there would be some charge imbalance only in a few nanometers, the whole millimeter volume of the capillary will flow. And by the way, that's also one application of electroosmosis. If you want to dosage 1 microliter, you turn on the electric field, and from the capillary you will get 1 microliter of liquid. Another example to better understand this, because this is, I have experienced typically difficult to understand, that really the whole fluid, even far from the surface where you already have charge negative flows. Imagine that you sit on a river of a bank and you have a lot of friends, and all of you start to paddle the water next to the bank, just in the first meter. And if you do it for a very long time, and if you forget about the friction of water with the riverbed, the whole river would start to flow even far from the bank where no one paddles. And that's exactly what's happening here, that the driving force is only at the interface. One short comment on the magnitude of the external field. In this work, we used the electric field, which was 2 to 10 times 10 to 8 volt per meter, which is something like a megavolt per centimeter, while in simulations typically a volt per centimeter is used. So why do we use such a strong field? The main reason is to have statistically meaningful results, because in experiments you can average 10 to 23 particles, while here we have hundreds of molecules in each layer. And here I show that we monitor this streaming velocity of the liquid as a function of distance. And at each distance, the velocity of any, let's say, water molecule has basically 2 components. One is this streaming velocity, the oriented flow, and the second is the thermal motion, and that goes with the velocity which is of the range of mean square velocity, and for liquid at room temperature, it's plus minus 370 meters per second. So of course you need some signal. And we simply selected the electric field to be so big because the magnitude of the electrosmotic mobility, you can't choose that. That's really the property of your system, and it's so small that simply only when you use such a big electric field, we end up at the average velocity, which is of the order of volts, and we can measure it. We can go 10 times slower and measure 0.3 plus minus 370, but we definitely cannot measure at 1,000 times smaller, which would be still 1,000 times larger than an experiment value, because we can't average 0.003 plus minus 300. It's simply impossible in the size of the system we used. So that's why we use such a strong field. But as long as the field is in the linear response regime, it means that the response is proportional to the stimuli, then we are safe, and we tested that in this case it was okay. So we can measure the streaming velocity, we can see that it's positive, negative, etc. And we can then report the results, and we directly measure the mobility as a function of the surface charge, but the experimentalist as well as us convert the mobility to zeta potential. The experimentalist immediately directly measure what's the pH. We used the pH titration data to convert the surface charge to pH. So we can report, like in the experiment, zeta potential as a function of pH. And here is the result. And already the first results for rubidium chloride were excellent because it has the right shape, going from positive to negative values with pH. It has the right magnitude. And also, if you decrease the concentration, the signal gets stronger. What I indicate here by zero mole means basically only counter ions. So if it's positively charged, I have only chlorine. If chloride, if it's negatively charged, I have sodium. If it's uncharged, I have literally 2 or 6 pairs of the salt. Then we did simulations for sodium chloride, and the first simulations for sodium chloride I got were these. And I was wondering for several months what's going on, because it definitely doesn't have the right shape. It stays positive even at high pH. And only I became a bit confident in my simulations when I did it again only with these counter ions, when really the shape became, in fact, in very good agreement, and even the values with the experimental data. So we got the agreement basically with experiment, at least at low concentrations. But the huge advantage of simulations is that not only you get the results, but you get the molecular view. And you can deduce the origin of the phenomena you see. And so in this case, we have seen what's the difference in case of sodium. And first of all, we were lucky to find these experimental data, because most titrations are done at a really small concentration of salt, but there is this acustophoresis, which can go to basically molar concentration. So there are also experimental data which see that the zeta potential at high concentrations, like we used in our simulations, can stay positive throughout the pH range. Then we did the same with divalent ion. Again, instead of going down at high concentration, it even went up. But we found also simulation at high concentration of another divalent ion, calcium chloride, which also show that it has this anomalous behavior, that the zeta potential can stay positive throughout the pH range. And here is the molecular explanation. And again, the movie's fine. We need to look at the bottom one. So we have seen before the top one, which was rubidium. And now on the bottom, you have also negatively charged surface, but sodium. Sodium is smaller. It absorbs stronger. It can interact stronger with the surface. So in fact, there is more adsorbed sodium than there was rubidium for the same surface. But you can see most of the sodium is so tightly adsorbed that it cannot move, in spite of being subject to this electric field. And so then there is this majority, few counter ions, and in fact, it's these counter ions which rule, which go to the left, which drag the water molecule with them, and that results in a negative mobility, which converts the positive zeta potential, and that's exactly what we have seen in our simulations, and that's this anomalous behavior. So we have explained the origin of this anomalous behavior, and it's related to overcharging of the surface. So I think I'm running out of time, so I will probably skip many slides, and I will just show that currently we are studying the adsorption and flow through graphene-based nanopores. We study different nanopores with different height, with different lengths, and the behavior really differs. It can be like 7, 9, 12 angstrom height. It can generate several layers of water and ions. And here I will show, and these pores can be easily manufactured because you basically take a piece of graphite, use few layers of graphene as a spacer, you cover it again with graphene, and here you have electron microscopy photo of a perfect graphene nanochannel, and if you have a battery of them, you can even do the flow experiments on them, and it's done in the National Graphene Institute in Manchester. And we currently are working on the application of these nanopores to capacitive deionization. And let me just describe that here we have a very thin nanopore, which is rectifying so strongly that if it's negatively charged, only positive ions can enter the pore, and it's basically impossible to go through for the cations, and the opposite is here for the positively charged surface, only anions can go through. And if we turn on the electric field, I think it was so fast that I will try to run it once again. If you turn on the electric field, the positive ions will move through this channel to this reservoir. The negative ions will move in this direction through the positively charged channel, and at the end up you do really this capacitive deionization that you basically remove all the ions, and you end up with less salty water, or basically desalinated. So because I'm sure I ran out of time, I will end up here. I wanted to show, I have a couple of slides showing the artifacts. If your electric field is too strong, maybe we can leave it for questions, but I think it's time to thank you for your attention.
Thank you very much, Milan. It was very interesting, great talk.
Sorry, I assume that students should ask questions, but I just wanted to have some clarification, because you were speaking about electric fields. And if you have, for instance, 2 electrodes and separate by electrolyte, you cannot have a static electric field because it will be screened by the double layers, and the bulk will be neutral. In order to have a static electric field there, you should have a flow of ions, background maybe ions, apart from your colloidal particles, and then they should react electrochemically at those electrodes. Then there will be a continuous current, and that continuous current will give you ohmic drop. Ohmic drop will give you electrical field, like that. So when you're speaking about static electric field, do you mean exactly like that or something else?
I think there is not a big difference between the experiments and simulation in this. Of course, for us, it's simply extra force we just turn on, and it's so easy to turn on. But you mean like the electrophoresis setup? Mm-hmm. So it's really, in ancient times, it was done really that there were 2 electrodes, and there was a static field with basically constant gradient between the 2 electrodes, and really the people were watching the particles as they move. They were monitoring on some CCD cameras, and of course the field is screened, but you simply have the voltage difference, you have the distance, so it's clear what's the electric field. So honestly, I don't fully understand what would be the problem, because really there was a constant static electric field. Of course, there were some reactions happening and electron transfer at the electrodes, but in the volume between the electrodes where the experiment is done, it was really constant field and constant speed, of course, plus minus thermal
the field
motion.
Will be there, but not if you have a blocking electrodes, right? If you don't have electrochemical reactions at the walls, then after you apply voltage, you will settle the double layers, but the bulk will be electroneutral. And so your motion of the particles will be diffusive, simply random, and then it's sucked at the double layer, but the double layers are narrow. So in order to have a permanent field like that, you need to have a permanent current, continuous current, in which ionic current is transferred into electronic current, like that one. So that's called an ohmic drop, like that. Ohmic drop will give you the electric field. And because of that understanding, I want to also understand when you apply very large fields, how they're related to this kind of overall phenomenon, because you have to consider the whole system, right? With conversion of electronic current into ionic.
We are lucky in this case that we use non-dissociative models of water, so even a strong electric field cannot break our water molecules, so that's to some extent advantage. And maybe I will just show here this slide saying that here I see for example, the density of ions in the pore and outside. And you can see here we used even weaker electric fields. And this purple one, that's definitely the strongest one. And in this case, I would say it's the only one which already introduces artifacts. For example, this is positively charged surface. There are no ions in it. But if you have so strong field, you start to have ions there. Or here you see the density profile of chloride. If the field is weak, basically the structure is independent of the electric field. If the electric field is too strong, you start to really deform the shape. So we take care of this. Of course, always there is at least some effect of the electric field. Simply water orients always, if you turn on electric field. So we are doing our best to use as small electric field as possible, but of course it's 5 to 6, 7 orders of magnitude larger than in reality.
Okay, but the origin of that electric field should be associated with the current which goes here, ohmic current, because otherwise you will not have electric field in the bulk.
Yes, but we use periodic boundary conditions, and the electric field is simply applied a priori, simply like external field. So we don't need to have the physical electrodes in our system.
Yeah, I understand. In simulation, you can do that. But in reality, you have to relate a voltage drop and electric field through the current and through electrochemical reactions taking place at the interface.
Yes.
Thank you.
Thank you very much. When you were using, I suppose you are using full-scale force field. So I saw on a negative surface, sodium is strongly binding. So in that case, what was the selectivity? I mean, aren't they overcharging? So
with full charges, definitely sodium was overcharged, but in fact we published several papers on this, and in the later paper we also scaled charges, and we also compared the adsorption and zeta potential behavior at TiO2, which is strong adsorbent. So you see this anomalous behavior of zeta potential with the pH, and we compared it with quartz, which was modeled with scaled charges, and there the behavior is absolutely standard. So definitely the model, if you scale strongly the ions adsorb, are the key factors which affect also the behavior of the zeta potential.
And what was the effect of electric field? Like the selectivity was changing?
You mean the magnitude of the electric field?
No. If you change electric field, so it might have different effects on cation and anion, so they might have different movement or the flux. So did that change the selectivity with respect to electric field?
I think we should discuss it in privately, because we always report the result of both ions. I cannot exactly say how much change in the behavior of cations and anions contributed. But in fact, at this extreme pH, basically it's either purely cation dominated or anion dominated.
And how much was the thickness of that stern layer?
Typically, it was really up to 15-20 angstroms from the surface, because we typically used concentrations up to, let's say, 0.4 molar. and even what I call zero mole meant that we needed to have counter ions, which were basically at the concentration of something like 0.06 mole.
And I see that the electric field is around 0.2 volt per nanometer. How do we compare that with some experiment? Because the electric field that we are using is around 0.06, and the size of my cell is around 18 nanometer. So we still think it's too much.
Of course, it's much, but I have seen to average the streaming velocity, I can't go much lower. Of course, some of these results are already a few years old, so we can go a bit lower. Once again, it's of the order of, let's say, 10 to 5, 10 to 6 volts per centimeter, while in the experiment, it's 1 volt per centimeter.
Okay, thank you.
All right. One more question? Short question.
And you assume that Cepher charge is uniform, yeah?
No, definitely not. It's a realistic charging. So, for example, if you want to make the surface charge negative, we adsorb more OH minus groups on the surface. And if you want to make it positively charged, we add hydrogens to some of the surface oxygen. So there are specific atomic charges on each titanium, oxygen, hydrogen ion, and they even change. It was calculated by ab initio, so it's really atomistic charging. There is nothing like just monotonous surface area, surface charge.
So you just only could say that it's positively or negatively charged, but not with more details. Yeah.
Yes, I wasn't talking about the details of the model, but yes, I report just the average surface charge density, which results from the atomic.
Okay, thank you very much, Milan. It was a great talk. Thank you for your attendance. We have a coffee break now, and please come back by 11:20. Thank you very much.
balloons with the money we've got. Set them free at the break of dawn. Till one by one they were gone. Back at base, box in the software. Flash the message, something's out there. Floating in the summer sky. 99 red balloons go by. Call the troops all in a hurry. This is what we've waited for. This is it, boys. This is war. The president is on the line. As 99 red balloons go by. 99 nights of the air. By super high-tech jet fighters. Everyone's a superhero. And everyone's a Captain Kirk. With others to identify. To clarify and classify. Scramble in the summer sky. It's 99 red balloons go. 99 dreams I have had. In everyone a red balloon. It's all over and I'm standing pretty. In this dust that was a city. If I could find a souvenir. Just to prove the world was here. And here is a red balloon. I think of you and let it go.
If there's anything you need, all you have to do is say, and you know, satisfy everything in me. We shouldn't waste a single day. So don't stop me falling, it's destiny's calling. A power I just can't deny. It's never changing. Can you hear me? I'm saying I want you for the rest of my life.
Together forever and never to part. Together forever with you. And don't you know I would move heaven and earth to be together forever let you down, there's always something I can do. Because I will never wanna see you frown. I'll always do what's best for you.
There ain't no mistaking, it's true love we're making, something to last for all time. It's never changing, can you hear me? I'm saying I want you for the rest of my life. Ooh, yeah.
Together forever and never to part. Together forever with you. And don't you know I would move heaven and earth to be together forever with you.
So don't stop me falling, it's destiny's calling, a power I just can't deny. It's never changing, can you hear me? I'm saying I want you for the rest of my life.
Together forever and never to part. Together forever with you. And don't you know I would move heaven and earth to be together forever with you. I'm going under and this time I feel there's no one to save me. This all or nothing really got away, driving me crazy. I need somebody to heal, somebody to know, somebody to have, somebody to hold. It's easy to say, but it's never the same. I guess I kinda like the way you numbed all the pain. Now the day bleeds into nightfall, then you're not here to get me through it all. I let my guard down, and then you pulled a rug. I was getting kinda used to being someone you love. I'm going under, and this time I feel there's no one to turn to. This all or nothing way of loving got me sleeping without you. Now I need somebody to know, somebody to heal, somebody to have, just to know how it feels. It's easy to say, but it's never the same. I guess I kinda like the way you helped me escape. Now the day bleeds into nightfall, and you're not here to get me through it all. I let my guard down, and then you pulled the rug. I was getting what's mine, yeah, inside out. Ooh, you got me inside out. Yeah, inside out. Ooh, you got me inside out, inside out. I'll play the game. Won't make the same mistakes. It's all the same. If we can give and take. Hold on, hold on, hold on. Hold on, hold on, hold on. Ooh, yeah. Inside out. Ooh, you got me inside out. Inside out. Ooh, you got me inside out. You got me inside out. And outside. You got me inside out. And outside. Inside out. Outside. Inside, outside. We were good, we were gold, kind of dream that can be sold. We were right till we weren't, build a home and watch it burn. I didn't wanna leave you, I didn't wanna lie. Started to cry, but then remembered I can buy myself flowers, write my name in the sand, talk to myself for hours, yeah, the things you don't understand. And I can take myself dancing, and I can hold my own hand, yeah, I can love me better than you can love me better, I can love me better, baby, can love me better, I in my name's cherry red, match the roses that you left, no remorse, no regret, I forgive every word you said. I didn't wanna leave you, baby, I didn't wanna fight, started to cry, but then remembered I can buy myself flowers, write my name in the sand, talk to myself for hours, yeah, say things you don't understand. And I can take myself dancing, and I can hold my own hand, yeah, I can love me better than you can love me better, I can love me better, baby, can love me better, I can love me better, baby, can love me better, I can love me better, baby, can love me better, I didn't wanna leave you, I didn't wanna fight, started to cry, but then remembered I can buy myself flowers, write my name in the sand, talk to myself for hours, yeah, the things you don't understand. And I can take myself dancing, yeah, and I can hold my own hand, yeah, I can love me better than, yeah, I can love me better than you can.
nerves that have just begun. Listen to Marvin all night long. This is the sound of my soul. This is the sound always slipping from my hands. Set a time of its own. Take your scissored arms and write a next line. Oh, I want the truth to be known. And know this much is true. And know this much is true. I bought a ticket to the world, but now I've come back again. Where do I find it hard to write the next line? Oh, I want the truth to be said. I know this much is true. And know this much is true.
If it takes forever, I will wait for you for 1,000 summers. I will wait for you till you're back beside me, till I'm holding you, till I hear you sigh here in my arms. Anywhere you wander, anywhere you go, every day remember how I love you so. In your heart, believe what in my heart I know, that forevermore I'll wait for you.
All right. Hangprobe. Okay. Okay, ladies and gentlemen, we are back. You probably realize that self-assembly is a key concept here at this conference and in science in general, because the molecules of liquids and everything, they are doing their job without human beings. So it's just self-organization of matter, what's going on around us in nature. But what happens if people think like engineers and they want to influence the behavior of matter? So our next speaker, Sofia Kantarovic, will talk about magnetic matters and what happens, how can you modify the behavior of that matter with some convenient way, specifically with magnetic field. Okay, so that's the topic of Sofia, and I would like to thank her for jumping in, because it was a last-minute solution because our original speaker couldn't come, unfortunately. So thank you very much for jumping in, and the floor is yours, Sofia.
Hi, everybody. Thank you for having me here on such a short notice. If you need me again, please let me know. So before we start going really deep into what I'm going to talk about and about magnetism and about all those things, I suggest I try to put myself within the scales that were introduced this morning. So Miguel, for instance, said in the beginning that there is this scale, right? So there are two axes, and then here comes the ab initio, here comes the atomistic simulation, here comes something hybrid coarse-grained, and there what people do. So this is me. I do that. That is what people do. I'm that people. So I'm doing that coarse grading that is exactly falling in that scale. So it would lack probably, in comparison to the previous two talks, would lack quite some chemical detail. But what I will try to convince you, though, is that it's not so bad. So those people also have the right to exist somehow. So, I mean, we justify our existence in the way I will tell you. And the story will be the following. So I would walk you through the points. So I would tell you about what magnetic soft matter is and why we think it is interesting. And there I would also try to convince you what exactly is needed to be done for it to be even more useful than it is now. Then I would introduce my methods. Then we would focus on two types of systems that are called multi-core magnetic nanoparticles and magnetic nanogels. And then finally, conclusions and outlook. So what is magnetic soft matter? Imagine that, there is an old joke dating back to 2011 to a liquid matter conference in Vienna, and that was done by Dan Frankel, whose name probably all of you know. And the joke was, what is soft matter? If you go to the airport, you can see this plastic bag filled with gels, etc., that you cannot bring on board unless it is in a given volume. So this all is soft matter. So that's exactly what you need, like, to minimize in volume in order to carry on board. So these are liquids, gels, pharmaceuticals, foods, dyes. I mean, whatever. It's really a lot of things. And now imagine that you want to have a biologically compatible control over soft matter. We heard a lot about pH, about extreme values of pH, about ionic transport this morning. But you don't want to have ionic transport or highly highly active electrophoresis in your blood vessels. That is very suboptimal. And what you need if you want to control or drag something through the blood vessels, you need a control engine that like manages to distantly, so from distance, actually transport those things. And magnetic is perfect to this extent. Why? Because it doesn't interfere with living tissues at all. So if you bind needed chemicals to a magnetic particle that is small enough, and we come to this in a moment, then hypothetically, with an applied magnetic field, you can transport this medicine to the target and then apply it there. How big should the particle be? So in order to penetrate the cell, it should overcome the brain barrier. So the brain-blood barrier for the cell is critical. So the particle cannot be larger than a micron, or better, does not exceed something like 200 nanometers, 500 nanometers in diameter. So that would be a good size. In general, people did not think about it in that terms 60 years ago. The first object that was synthesized as magnetic soft matter, and I'm trying to use the pointer, there was a ferrofluid. What is a ferrofluid? Ferrofluid was synthesized by Ron Rosenzweig and his colleagues as an aircraft fuel. It was a very ambitious idea and project of NASA that never worked, but the impact remained. And the story is that these are magnetic nanoparticles, approximately between 10 and 50 nanometers in diameter, suspended in a liquid carrier. And then if you put such a magnetic fluid on a substrate in a petri dish, and you put magnet from below, what you have magnetic field lines going through the fluid, magnetic nanoparticles trying to follow the field lines, the surface tension of the fluid pulling them back, and that's what you see that got the name, That's what got the name of Rosenzweig instability, that hedgehog. That was 1964. Since then, synthesis went up, and so did the applications of those magnetic nanoparticles suspended in liquid carriers. And coming back to what I started with, the idea of biomedical applications is probably nowadays the most important ones in the whole story of magnetic soft matter. So you can do particles like ellipsoids, platelets. You can take magnetic nanoparticles and glue them rigidly together to build multi-core particles, or so-called nanoflowers. You can connect them into polymer-like structures where each monomer is a magnetic nanoparticle. And all this basically is done in order to optimize the heating properties. So because when you bring a magnetic nanoparticle to a certain place with an AC field, you can rotate this magnetic nanoparticle and it will locally hit the target. This is called magnetic hypothermia. It's not necessarily to treat cancer, as you might think, or that people usually claim it is for. Actually, any heating or any mixing would work with this purpose, so with this kind of mechanism. Another thing is the transport process. So if I can transport these pharmaceuticals. And another advantage of this kind of heating or transport is that it is extremely localized. So unlike chemotherapy for cancer, for instance, that affects also healthy cells, local heating affects only tumor cells because the particles are held basically inside the tumor. So now, what kind of particles should that be in order to optimize the heating? And that would be the question that we would try to answer at the end of this presentation. So how do I design a particle that being transported to a target actually heats properly? And in order to do this, I will use that molecular dynamics simulations. And let me tell you a little more about the method. So basically, I would use only two basic potentials. So it's a very simplified, very coarse-grained model. So my particles would have excluded volume. That will be modeled by Lennard-Jones potential that is truncated and shifted. That is called WCA, Weeks-Chandler-Anderson potential. And the second one would be dipole-dipole potential. That is the interaction of two perfectly magnetized spheres. In this situation, my system can be characterized by two important parameters that I want you to remember. One is so-called lambda parameter, and it characterizes the dipolar interaction, so the interaction of two core-line dipoles, m, whose value is m, to thermal energy and divided by size. So it's a dimensional ratio of dipole interaction to thermal energy. And the second parameter is the concentration. As long as we are now on a nanometer scale, we have to take into account that the entropy and the interactions are competing both when structure of these systems is formed and when they respond to applied stimuli. So that's why we will operate this parameter and this parameter. I will show you a little later that this is not really all that simple. So, but what if I want now, instead of a spherical particle, to have a particle that has an exotic shape, say an ellipsoid or a platelet? In this situation, technically you have two options. So first, you can model a shape as a closed potential if this shape is geometrically describable, like a superquadric, for instance, like a superball. That you can do. Then you can plug in something that looks like Weeks-Chandler-Anderson potential, but contains some more elaborated distance expressions. So in principle, you can do that. But there are very few shapes that can be described that way. So one of the basically simplest and cheapest approaches is to build your shape out of spherical particles. And then you rigidly bind them together so that they stay in this shape throughout your molecular dynamics simulations. Alternative method would be to have a geometrical shape which is not a closed form of a function, and then on each step to solve a system of algebraic equations whether or not you have an overlap. And this is too costly, way too costly to do that. So in this sense, having those particles bound together is an advantage in terms of calculational speed, but it also has extra advantage. So for instance, if you don't want to have only a point dipole that is in the center of this particle, but you have some distributed set of dipoles within these particles, you can assign to each of these Rossby bead, they're called Rossby representations for obvious reasons. Each Rossby bead can have basically a dipole moment. So this is what we do. And in this situation, what you need to remember is basically that lambda really shows that head-to-tail orientation of dipoles is good, that anti-parallel orientation is still not bad, but then parallel and most like nose-to-nose configurations are really bad. And please, we are not talking about sauna and being wrapped and not being wrapped here. So it's just exclusively talking about the orientation of dipoles, okay? So I mean, I missed the starting point of that discussion, but I'm afraid of causing some reactions there. So what does the Zeeman interaction do to the dipole moment? It tries, as an applied field, I lost here, so it tries to align the dipole moment along the field direction. So these are the basic interactions. Okay, let's go to a more interesting stuff. So what do we know about magnetic nanoparticles and liquid carriers? We know that due to these dipolar-dipole interactions, even in the absence of an external field, if magnetic interactions are stronger than thermal interactions, those particles will form chains that clearly are head to tail, and they're lovely. But even better, if lambda is higher, is even stronger magnetic interaction in the system, they will form rings. So chains and rings. Right. So do we want to have chains and rings in blood vessels? Well, it depends on their size. In principle, it's not such a bad thing, particularly considering the chain is very responsive to an applied field. But what about rings? Rings are not. Rings are closed form. They have a zero magnetic moment. So rings are bad. Okay, now, can we quantify that? So let's assume a very simple model. You have a magnetic particle, it has a magnetic moment, and if an AC field applied, then the magnetic moment due to Zeeman energy follows the applied field, but it is so rigidly bound to the particle body that the whole particle rotates. It's a point dipole approximation. So what happens in this condition? It is the whole particle rotation. So we have a full particle rotation, it causes friction, that is how the heat is generated. Now, what do we know about this? We can measure in a system the magnetic moment autocorrelation function. It will look like this, and it is characterized as an autocorrelation function of the magnetization of a particle or of the whole system with respect to its zero moment orientation. And this very C of t, once it is Fourier transformed, will give you the so-called dynamic susceptibility. That is very similar, if you're acquainted with broadband dielectric spectroscopy, is exactly the same expression as there. So it's exactly the same approach. And it is, of course, just a linear response approximation for that. So what is important there? The important part is this guy. So the imaginary part of the dynamic susceptibility is what is responsible for the power loss. So the dissipation, this is the dissipation, is what shows you a resonance frequency on which the applied field should be applied in order to reach the maximum heating. So the position of the maximum of the imaginary part of the susceptibility is what you are interested in overall. So this is what we will be looking at. Right, so we have, in a simple case, so if particles do not interact, we have a classical dBi spectra, a monodispersed spectra, a polydispersed spectra. This is a real part of the susceptibility, this is the imaginary part, and you have only one maximum. This maximum is responsible for this, so it is exactly located on the frequency that is inverse Brownian relaxation time. That is the rotation, and the Brownian relaxation time depends on the viscosity and the volume of the particle. Right. Now, if instead you start adding some interactions, the dBi spectra, the classical dBi spectra, changes, and changes pretty much. So you can see that the position and the height of the imaginary susceptibility changes. Now let's try to understand how exactly it changes. We did quite some simulations to that extent, and we discovered that if you increase the interactions and chains and rings are formed, either branch structures at high density, what happens is that a single peak, a single debian peak of the imaginary susceptibility actually splits in two. There are two peaks, so it means that there are two eigenfrequencies in the system. Which kind of frequencies are that? So one is the rotation of the whole cluster. So the whole cluster rotates, and this comes lower than a single particle Brownian rotation. However, within this cluster, the particle vibrates, it leaves, and this goes higher than the Brownian relaxation. So it's a higher frequency process. So by interactions, solely interactions of a point dipole particles, you can split already the spectra of the dynamic susceptibility into two maxima of the imaginary part. What does it tell us? It actually tells us that you can both hit on this frequency and on this frequency. why frequency is important and not only the amplitude of the field. There is a physiological limit of a patient which frequency and which strength of the field you can apply. It's called so-called Brezovich criteria. I mean, it is arguable, but is one of the references that is currently on the market. And this is the product of frequency times the amplitude. If the particles are very strongly interacting and they are forming rings, in principle, the frequency they will be susceptible to is quite low. But the problem is that they are already clustered in rings, as we talked previously, and this makes them magnetically very reluctant to the applied field. So they wouldn't. So you need a strong field. Instead, those local frequencies, the whole cluster will not feel that kind of perturbation. But this oscillation will change. But then, again, you need a very high frequency. So point dipole is, in general, a very simplified approximation. Why? Because we know that magnetic particle is not only what that people on that side of the spectra do, but also what chemists do, and it has a crystalline structure. And it means that there are directions within a crystalline lattice that are easier to magnetize than another due to exchange interaction, due to spin-spin interaction. So what happens there? It means that the particle, each magnetic particle, has two mechanisms to relax. One is the whole particle rotates, as we said, Brownian mechanism, but another option is when the magnetization actually jumps inside the body of the particle. And this is so-called Niel relaxation. This Niel relaxation is much faster and it only matters if the particle is small enough and the crystalline anisotropy is weak enough. So basically, if you even have a single particle that allows you both relaxation mechanisms, you immediately get a split of the spectra, because there is a frequency on which the Niel relaxation is agitated, and there is a frequency at which still the Brownian relaxation is agitated. So we're having already two. Now, but it has exactly the same problem. Niel relaxing particles are super small. Brownian relaxing particles are large and highly interacting. And the idea came, first of all, we need in our simulations to get rid of this single dipole approximation and do something more. The problem is, look at the time scales. They're several of orders of magnitude apart. So what kind of time step would you need to integrate your equation of motions to reproduce both time scales? It's a challenge, it's a technical challenge. And the second thing is that maybe we need to play on the anisotropy, on the internal anisotropy, and go somewhere in between and find the right frequency, or at least the right spectrum. So we proposed three different mechanisms how to take into account the internal anisotropy. One is the simplistic one. This is an ideal superparamagnetic particle. So it's infinitely polarizable. So the field applied, and it has a non-linear reaction to the field, but the point dipole always will point in the direction of an applied field unless there are dipolar fields in the system and interactions. The other model is based on basically solid-state physics, and this is related to Stoner-Wolfert approach. And this relies on two minimum states. So you have an easy axis of magnetization, so there is a crystalline lattice favorable orientation of the magnetization, and it can only switch within this orientation depending on the energy barrier. However, for nanoparticles, you need to add thermal perturbations, so you add on top of it a probability of a switch that is not related to an applied magnetic field. So you combine technically molecular dynamics with a Monte Carlo step. So you do equation of motion, you calculate the field acting on each particle, you calculate the probability of a switch, you either switch or you don't switch. This is good model, very fast working model for very anisotropic particles. When the particles are not then anisotropic, you don't expect two-state model to work properly. So instead of being either here or here, the magnetization can actually have a precession around the easy axis. And this is a frequency, this is its own frequency of oscillations that has to be taken into account. And then it can also point outwards of the easy axis. And for that, it took us several years of work, but we combined the solution of Brownian dynamics with a solution of Landau-Lifshitz-Hilbert equation. So it's a so-called egg model. So you model the dynamics of the magnetic moment that is connected by a spring to the whole particle. And that's why it looks like an egg, like a yolk, right? And the yellow part is rotating with friction, with viscous friction inside. So this is a moment, and the whole particle is an egg. And in this situation, what you have really an accurate solution of Landau-Lifshitz-Gilbert equation. So you get very accurate magnetization dynamics. Of course, you need to go to the time step that resolves Landau-Lifshitz-Gilbert time step, right? Or you update, so you do a combined step, so not exactly the same step for molecular dynamics and the solution of Landau-Lifshitz-Gilbert. So, what do we get? First idea that was probably proposed something 15 years ago, let's glue the particles together. Let's build so-called multi-core particles. What will we get in this situation? We will get cores that are rigidly bound in a polymer shell, or it can be just like they're chemically glued together. They have no Brownian degrees of freedom per se. The whole colloid has, though, a rotational degree of freedom. There are a lot of discussions going on whether or not you need or not need the exchange interaction between the cores. So far, people think that it matters, but not that much. We will not consider that. So this is a so-called nanoflower. So these are our colleagues from Sorbonne. This is from the group of Ladislav Ekos from Timisoara. Right. So we modeled them, as I said, as a raspberry. We already had an approach. And each core now has its own anisotropy. So the model is like that. So you have a multi-core particle. Each core has an anisotropy axis. And what I do, I let those particles relax, and I change the lambda, the interaction between the cores, and the anisotropy that is characterized by a parameter kappa. Kappa is the energy, the anisotropy energy that is proportional to the volume divided by the thermal energy. So when you have small anisotropy and small interaction, what basically you have a red spectra of the angles between the easy axis and the orientation of the dipole. No interactions, no anisotropy manage to create a preferred orientation of the magnetization inside the multicore. If the interactions are very weak, but the anisotropy is very high, all dipoles are oriented along the anisotropy axis. There is a very interesting intermediate state. When the interaction is strong, and the anisotropy is strong, and then you start seeing the competition. If instead the interaction is very strong, and no matter how anisotropic is, the anisotropy cannot anymore hold any ordering of the dipole moments. How is it reflected in the susceptibility? It turns out that the higher the susceptibility of the so the higher the interaction between the cores in the multicore is, the lower is the susceptibility. So the interactions block the cores, and when you apply the field, there is no way you can go out. And if you look at this part, you will see that the same effect has the anisotropy if the interactions are weak. But if the interactions are strong, the anisotropy leads to a slight increase in susceptibility. So because it blocks the interactions, so it keeps the dipoles inside relatively disordered. So what happens in the spectrum? There are a lot of curves. I don't want you to look at all of them. Well, of course, I want you to look at all of them, but I just want you to understand several ones. So, if the interaction is small and the anisotropy is small, you get a perfect Debye spectra. One peak, nothing matters. The peak will be at the eigen frequency of a single core. If you have very weak interactions and very strong anisotropy, it's basically a Debye spectra with a peak that is the rotation of the whole multi-core particle, because everything else is blocked by the anisotropy inside the cores. Right. And what happens here is that you still see a small appearance of this. And this is the second peak. This is the high frequency peak that is related to a single core. So, and you can see, if you look at this position, it's at 1, and at this position here, and now you compare it to this position and this position. So this is very strongly interacting cores. What happened to this peak position? It shifted towards higher frequencies. This peak that is related to the rotation of the whole multi-core as total doesn't change the position. And it's clear because the size of the multi-core and the viscosity of the fluid is not affected by the internal structure. So take-home message from this spectra is, by tuning both interactions and anisotropy, you can very strongly change, look here, it's the most interesting case again, intermediate interactions, intermediate anisotropy. You can have a very strong shift of this eigenfrequency of the core. So you get actually the least distance between those. You can even get rid fully of the Brownian relaxation in this situation, because it would be too slow. So, in comparison to that. So, if you calculate the specific loss power, you will see that for low interactions, you get very nice, very clear, like saturation. So you basically have only those frequencies to maximize. But as soon as you start getting a plateau, that suggests you a new frequency. So, and you can see that you start having those oscillations in this regime. Again, if you go to two strong interactions, you're again in a two-plateau system. But this is the point where one can try to tune it more accurately. Right, this was a rigid assembly. Let me drive you rapidly through a non-rigid assembly. This is a magnetic nanogel. It's a polymer matrix in which the magnetic particles are embedded and can move. So unlike the cores of a multi-core, these guys are mobile. They can't freely rotate because they're penalized by the elastic matrix. I promised to dance, so and basically what happens here is that you add on top of a rotational Brownian frequency, you have also an elastic frequency of the matrix that can be manipulated in order to access some different peaks. So what do we get here? Let's stick to point dipoles, which is have this frequency, their own frequency, and again, the gel still has a frequency of its own rotation as a colloidal particle, even though it's of course very different from a hard ball. So soft colloid and hard colloid in a liquid, they of course have different Brownian relaxation mechanisms, right? So they do it differently because in one case, the solvent is not penetrating into a colloid, and in this case, the solvent can go through. It's basically a hydrogel with magnetic nanoparticles in it. How do we model it? So this is our spherical horse in vacuum. This is how we imagine polymers. So they're beads connected by springs, and we use that to create a nanogel. So we put our polymers into a spherical confinement, we let them relax. It's similar to what is called emulsion synthesis. So when polymers are injected in droplets And then cross-linkers are injected in those droplets, and then the cross-linking is occurring within the droplet. And that creates you pretty monodisperse nanogels. And the magnetic particles are chemically bound to polymers. We do it even simpler, which is take a couple of beads and announce them magnetic. So for us, that is what we need. And we also play with the morphology. So we can do Gaussian, inverse Gaussian, so it's a core, basically core is, so it's a vesicle, so it has an empty core and a shell, and dense core and a corona, or a uniform distribution of cross-linkers. And we calculate first the normal susceptibility. And what we see here, we see a very clear tendency. So the less cross-linkers you have, for weak magnetic particles, you basically see very slow, very low effect of interactions here. These strongly cross-linked systems induce proximity of magnetic particles that are in the gel. So the more it is cross-linked, the more closer they tend to be. If the magnetism instead is strong, in a weakly cross-linked gel, the magnetic particles have a lot of degrees of freedom, and they can cluster as they want and close into rings. And so the static susceptibility for highly interacting particles with a growing quantity of magnetic particles goes down, as for non-embedded into a gel matrix particles. But if the cross-linking is strong enough, then the elastic matrix stops particles from aggregating, and the susceptibility doesn't really go down. What happens on the dynamic spectrum? This is a very difficult, so this is really a very computationally costly approach, so we had to have an adaptive step to calculate those magnetization autocorrelation functions, because the difference in the time scales of a single particle relaxation, magnetic particle, and the whole gel is really different. The red curve is the experimental result for nanogels with the same magnetic content and uniform distribution of cross-linkers. So you can see two things. You can see that the eigenfrequency of rotation is very similar. It's a very similar effect, like if particles are clustered. So the frequency is very high. So it's a very, very fast vibration inside the gel. And the oscillation of the gel are very slow. So you again have a very clear split that mildly can be actually tuned by the cross-linker distribution, but clearly only very mildly. So I'm wrapping up. What did we see? I remind you, right? Where did we start? We started that we want these magnetic particles of some kind to actually hit. For that, we need to have a full control over not only the position, but also the height of the imaginary part, of the maximum of the imaginary part of the dynamic susceptibility. And because that is what gives you the heat production. Debye says you have Brownian relaxation, you have one peak heat on that. If we assume a Debye model for a real magnetic fluid or for a real system that will be used in mice or even in patients, that would be utterly wrong. That is clear. Even if you assume a superposition of Debyes, this is not the case. So what we saw instead was this. So first, you have an interplay between this Néel and Brownian mechanism that can be further enhanced by introducing accurate description of anisotropy of the cores, so playing between the size of the time scale of Néel and Brownian relaxations. You can also play by actually changing the concentration of cross-linkers or magnetic content inside a soft colloid. In principle, that is less controllable. You can control the aggregation. And all this never gives you a single Debye peak. None of them are Debye. So take-home messages are this. So even weak interactions need to be taken into account when describing dynamic specters. For multi-core particles, you really need to fine-tune the interplay between the interaction of the cores and the anisotropy. And this is material problem. So you need to have a certain number of cores, a certain size of the multi-core particle, and a certain really composition that allows such a unique combination. And it's not a trivial task. And in nanogels, they are good for transport because they're porous and they can contain a lot of substance, but they are almost uncontrollable in this sense. So it's very difficult to tune their dynamic response. However, so the main conclusion is if you wanna find or tune this resonance frequency of the or eigenfrequency of the system, still these three parameters can be very valuable and very useful. That probably is something that has not been considered yet in basically ensemble of properties. I want to thank people involved in this work, people from the University of Vienna, from the Ural Federal University, and Field Camp from the University of Edinburgh, and you for your attention.
Thank you very much. It was a very nice talk. And okay, we have our first question.
Hi, thank you very much for your talk. I really like gels and your gels, magnetic gels. What I have an understanding is, okay, you have say chain A and chain B, so they are entangled just with in terms of magnetic force, right?
Not quite.
Not quite.
So basically, what happens is that you chemically cross-link them necessarily. So, I mean, you can have physical gels that are due to magnetic interactions, but they're very unstable. So any flow will just disentangle constructions.
So it's a kind of collaboration with magnetic field and covalent.
Yes,
bond.
so the cross-linkers are covalent bonds for sure. That is necessary. And then what you need, I mean, that's what they do for hydrogels. So I'm talking about those PNIPAM things. And what they do, they also chemically bind magnetic particles. So they're not trapped in the pockets, because that is a very important part. If they're not chemically bound to an elastic matrix, their rotation is not at all constrained by being in a polymer matrix. It's just the viscosity of a solvent where they're rotating. So there is no impact of the elasticity of the polymer.
Okay, that makes sense. Thank you.
Any more question? Alexei?
Just you were speaking about the usage of rotation for heating. Will it disturb the system, actually? Because, for instance, if you implanted all these particles somewhere, right, and then you utilize absorption within the particle due to internal rotation of the spin, that's one thing. You kind of disturb surrounding less. Whereas if the particle as a whole starts rotating, it may be some consequences for your tissues, no?
In general, what people want, they want what is the right emphasis of apoptosis of those cells. So if they're mechanically disrupted, even better. So that is not that bad. That is good. And if people are not using it within a tumor, but using for, say, industrial heating and melting of a polymer by those particles, which is now a very hot topic for some reason. I don't know why they came to it now again, but it became again a very subject to discuss. And there you particularly need to disrupt. So there actually mechanical disruption of the polymer bonds is exactly what you need for melting those systems, to enhance melting. So if you need to locally instead measure the viscosity of a cell, because some cancerous cells have a different viscosity, also it's an indication for this liquid-liquid phase separation in cells that is also particularly hot nowadays. But there you can measure local viscosity in different parts of the cell with a magnetic particle. There you don't need a disruption. But there you also necessarily don't need an internal relaxation, because otherwise the viscosity measurements would not be exact.
And at the beginning you were speaking about the delivery of the particles with magnetic field. Is it realistic, or people intend to inject, these particles, particularly in the tumor, or how is going to happen?
So,
they use some kind of surfactant specific or antigens that will bring those particles to the tumor through the blood?
So thanks to Paul, we had a recent update from Pankhurst in Eger on that. And injection is working already on patients. So that is already clinically approved. So that part of hypothermia is working. What is not clinically approved is a clot disruption for Alzheimer by transporting the magnetic clusters and really mechanically disrupting those bilayers, so that those stuck layers. Now, magnetic gels are used for experimental patients and experimental treatments for transport. That works. And also porous particles filled with magnetic nanoparticles are used in blood vessels to be transported in gradient fields. So that is done. It's not medically approved, and it will probably take another 15 years, if ever. But it is realistic. It is working. So you just need really very, very, very subtle interplay, and you need liters of those systems if you want them to work in actual application. So you need a method. So first you need a recipe, but then you need a chemical method.
Injections work, as you said.
Injections work. All surface tumors, brain tumors, breast tumors.
What is the success rate?
Very high. So it's a very high ratio. I mean, at least what Pankhurst showed, right? I mean, what people actually owing the machines say. They say that the enhancement of treatment is very high. So also they make millions on that. I would be very surprised if they say, oh, we inject these magnetic particles and nothing damned work. I mean, it would be very weird. So I don't think they would say that. But at least literature says there is a huge enhancement.
Okay. Thank you.
Hi, first of all, it's a very interesting talk. I really enjoyed it. Thank you. Coming from a synthetic perspective, I knew that the nanograins are particularly important in these types of systems. And I've always wondered what's the temperature effect in affecting these systems? Because some magnetized systems, they can have hysteresis loss in the magnetization curve. What's your take on this?
That's a beautiful question. Yes. So you need to find magnetic material whose Curie temperature is far away from any heating range you're working at. If you get a transition from a ferromagnet, say, or so from a anti-ferromagnet, anti-ferrimagnet, anything with a remanence, to something that becomes super paramagnetic, so you destroy the spin ordering, you're screwed. Because there is nothing, and you can't take out those particles anymore, because, I mean, unless the destruction of spin order is reversible for some reason, like, so it's a very smart material, but usually once it's like destroyed, it's destroyed, and then you can take the particles out. So I mean, what people do, they still use biodegradable iron oxides so that they can be like changed into ferritin and whatever, so that the body actually, so the patient doesn't die from cirrhosis. I mean, not from cancer, but from cirrhosis is still not the optimal thing, right? If all this metal goes to liver, you don't want that. But I mean, there probably, if it gets demagnetized, it's even better. But still, yeah. So it's a very accurate choice of Curie temperatures, and you can quite tune them. So in this sense, you can tune particularly in multi-cores. That is a very easy thing, because if you allow exchange interaction between the grains, you can really very accurately tune that.
Thank you so much.
Thank you. So, any additional question? No. In that case, let's thank Sophia for this beautiful lecture. Yep. And let me close this session with a couple of remarks. I think we heard 3 very, very interesting talks. My impression is that the basic idea of having a couple of elongated talks at conferences to support understanding for students and non-students, it might be an idea that might be inherited by later EMLG conferences. All right, with that notion, I would like to close this session and see you in the evening session. Thank you very much.